Hello and good evening to everyone, guys. I welcome you all to this wonderful channel by Unacademy NEET English. Well, my name is Khurshid Alam and you can also call me KK Sir. Now, I hope you all are doing great, but before we move ahead, let me know in the chats if I am visible and audible to each and everyone. Let me know in the chats quickly. Let me know in the chats if I am audible and visible to each and everyone. Let me know in the chats quick. Yes, quickly. Let me know in the chats. Okay. I believe that we are live now, and we simply let me tell you that as we are live now, and in today's session we will be discussing a very important chapter of organic chemistry, that's aldehydes, ketones and carboxylic acids. In this session we will be discussing this chapter in detail so that no question can even dare to bother you in upcoming NEET examination or any other competitive examination. Let me tell you, if you have not studied this chapter yet, be with me as we will kick off this session very nicely. So, before starting the chapter, let me know, are you super excited for today's session? And how is the Josh? And how is the Josh? My dear lovely students, let me know in the chats. How is the Josh? We will try to complete this chapter in 4 hours, but it may be less than, say 4 hours, or it may be slightly more than 4 hours. Okay, let me know in the chats. How is the Josh? How is the Josh? Are you super excited? Are you super excited? Let me know in the chats so that we can move ahead and start today's session. Let me know in the chats, guys. Let me know in the chats. How is the Josh? How is the Josh? And I would want you all, guys, to mark the attendance by smashing the like button. Come on, smash the like button as well. And also share the link of today's session with your friends as well, so that they will also get benefited. Okay, let's get going. So here is our, first topic, that is methods of preparation of aldehydes and ketones. We know the chapter is aldehyde, ketone and carboxylic acids. We will finish first aldehydes and ketones, and after that we will finish carboxylic acids. Now, first is methods of preparation of both aldehydes and ketones by oxidation of alcohols. As you know, we have already completed the chapter alcohol in last session, so we have already discussed these types of reactions there. Now, let me show you once again a little bit. That means this is by oxidation of alcohols. Now the question is, which alcohol can form aldehyde and ketone, and with the help of which reagents? Remember, first of all, we must know that if we are having a primary alcohol, on treatment of this primary alcohol with mild oxidizing agents, because if we use strong oxidizing agents, primary alcohol will form carboxylic acid, but we have to form aldehyde or ketone. So first of all, primary alcohol on treatment with mild oxidizing agent results in the formation of aldehyde. Now have a look. What you have to do is, this is very simple reaction. You have to remove one alpha hydrogen and one hydrogen from this functional group, so that carbon and oxygen forms a double bond. So primary alcohol results in the formation of aldehyde with same number of what we call carbons as that of this parent alcohol. Same number of carbons are present in aldehyde as that of parent alcohol. Similarly, if you are having a secondary alcohol, same trick you can apply same trick. What you have to do is, on treatment with mild oxidizing agent, you have to remove one hydrogen from alpha carbon, that means one alpha hydrogen, and one hydrogen from functional group, so that carbon and oxygen can form a double bond. That means it will result in the formation of a ketone having same number of carbon atoms. So primary alcohol results in the formation of aldehyde, and secondary alcohol results in the formation of ketone. Let me show you some examples. Say for example, we are having an alcohol like this. We are having an alcohol like this. This is a primary alcohol. What we have to do? We have to treat this with mild oxidizing agents. And what is the trick? You have to remove hydrogen from functional group. So let me show you like this. This is the hydrogen and this is the hydrogen. We have to remove. What we have to remove is, we have to remove this hydrogen. We have to break OH bond. We have to remove this hydrogen from functional group, and we have to break this alpha carbon and alpha hydrogen bond. That means we have to remove hydrogen from alpha carbon. Now this oxygen and this carbon then forms a multiple bond, which means it results in the formation of CH3. Then it is CH double bond O. So it is CH double bond O, or we can write down this in this fashion, CH3C double bond O, and this is having H. So primary alcohol results in the formation of aldehyde. Now the question is, what are these mild oxidizing agents? Let me tell you, mild oxidizing agents which we can use for this conversion, for conversion of primary alcohol to aldehyde, or for conversion of secondary alcohol to ketone. Mild oxidizing agents are, number one, it's Serret's reagent. I've already discussed this reaction in alcohols. So one is Serret's reagent. Second is Colin's reagent, or you can use Corey's reagent. Corey's reagent is also known as pyridinium chlorochromate, that means PCC, pyridinium chlorochromate, PCC. Similarly, you can use pyridinium dichromate, that means PDC, or you can use chromium trioxide, but remember in anhydrous medium. But the most important reagent, or the most common reagent for conversion of primary alcohol to aldehyde, or for conversion of secondary alcohol to ketone, is, guys, that is what we call Corey's reagent. So this is the most common reagent for conversion of primary alcohol to aldehyde, or for conversion of secondary alcohol to ketone. So this was the example of primary alcohol. Let me show you another example of secondary alcohol. For example, you are having this alcohol, secondary alcohol. Now if I write down like this, what we have to do is, we have to simply remove one hydrogen. That means we have to cleave O and H bond, one hydrogen from functional group and one hydrogen from what we call alpha carbon. Now after that, on treatment with mild oxidizing agent, after that, what will be the product? Product will be simply this carbon. When we remove hydrogen from this carbon and hydrogen from this oxygen, this carbon and oxygen will form a double bond. So this is simply what we call a ketone. So secondary alcohol results in the formation of ketone having same number of carbon atoms. So this was a secondary alcohol. Similarly, if I write down like this, this is CH2OH. What you have to do is convert this CH2OH into CHO functional group. You can write down directly that you have to convert CH2OH functional group, this CH2OH group into CHO group. That means you have to convert this CH2OH into CHO. You can also convert in this fashion, or you can use this trick, or you can use this trick. So mild oxidizing agent. Similarly, if you are having a secondary alcohol, then you have to convert this C single bond OH bond into C double bond O. This is, say a secondary alcohol is converted to simply ketone. So you will get like this. So primary alcohol into aldehyde, secondary alcohol into ketone. This is another trick that converts CH2OH into CHO or convert this COH bond into C double bond O. I hope this is clear to everyone. Let me know in the chats quickly. Let me know in the chats quickly. Is this clear? Is this clear to everyone? Let me know in the chats. Good evening, good evening. Good evening everyone. Good evening. Now, let me know in the chats quickly. Is this clear to everyone? And share this link with your friends as well. Come on. And you have to be very much sincere today because this is the very important chapter as per NEET is concerned or any competitive examination is concerned. Now, come on, tell me, is this clear to everyone? Yes, this is clear. Now, another reaction is or another preparation is by dehydrogenation of alcohols. Once again, it means you have to treat this primary alcohol once again or a secondary alcohol. Primary alcohol or a secondary alcohol. You have to treat primary alcohol or secondary alcohol to copper, or you have to, say heat primary alcohol or secondary alcohol with copper. That means here dehydrogenation takes place because we have already studied this reaction in alcohol, what we call in last session. We know that secondary alcohol undergoes dehydration. But here the question is you have to dehydrogenate alcohol. So that's why if you treat primary alcohol or secondary alcohol with copper at temperature of 573 Kelvin, what will happen? Once again, dehydrogenation will take place. That means you have to remove one hydrogen from functional group, one hydrogen from alpha position, one hydrogen from functional group, one hydrogen from alpha position. That means it once again results in the formation of primary alcohol will give aldehyde as well as hydrogen will be lost. That means dehydrogenation will take place and secondary alcohol will result in the formation of ketone and there will be also dehydrogenation. I hope this is clear to everyone. This is similar reaction as that of this. Only difference is here oxidizing agents were different and here it is copper but the products of reactions will be same. Now another reaction is or another preparation is from hydrocarbons. Now we know we have already completed hydrocarbons. That means reactions from those reactions with the help of which we can convert hydrocarbon to aldehyde or ketone. We have already studied those reactions. Now here by hydration of alkynes, you know hydration means addition of water, and addition of water or hydration of alkyne is known as Kocherow's reaction. This is known as Kocherow's reaction. We have already discussed this reaction as well. Now say for example you are having an alkyne. Say you are having alkyne, unsymmetrical alkyne. Whenever you add water to unsymmetrical alkyne, it generally takes place in presence of HgSO4 or H2SO4 dilute. And we know this addition of water across carbon-carbon triple bond is according to Markovnikov's rule. What was Markovnikov's rule? Negative part of addendum goes to that carbon-carbon triple bond which is having lesser number of hydrogen. That means it results in the formation of enol. It results in the formation of enol first. Now, after that, this enol will tautomerize. This enol will tautomerize and will result in the formation of RC double bond OCH3. So, this is basically the reaction. Now, you can simply use trick. Now, have a look what you have to do. This is, an unsymmetrical alkyne. Now, first of all, you just break. Have a look. Unsymmetrical alkyne, break two bonds. That means you first form single bond between these carbons. After that, have a look. You have to add water. Add oxygen of water to that carbon which is having lesser number of hydrogen. That means add oxygen in the form of a double bond O and add two hydrogens to other carbon. That means add two hydrogens to this carbon. So this is RCOCH3. This is what we call the product of this reaction. So this is the trick. You have to break two bonds between carbon-carbon triple bond. That means carbon-carbon triple bond will convert to carbon-carbon single bond. After that, you have to add water. But in this fashion, that add oxygen to that carbon-carbon triple bond or form double bond with oxygen. But oxygen will form double bond with that carbon-carbon triple bond which is having lesser number of hydrogen, and other two hydrogens will go to that carbon-carbon triple bond which is having more number of hydrogens. That means it will be like this. Now have a look. If you are having an alkyne like this, this is a symmetrical alkyne. This is a symmetrical alkyne. Now when you add water to this symmetrical alkyne, in presence of HgSO4, H2SO4 at a temperature of 333 Kelvin, what you have to do? You have to add water across carbon-carbon triple bond. But if it is unsymmetrical, then water will be added according to Markovnikov's rule. But as this is symmetrical, then we simply break one pi bond. That means it will become a double bond. After that, we will add hydrogen to one carbon and OH to another carbon. Simple. Or you can add this OH to this carbon, or you can add H to this carbon. So it's our choice. Now, after that, it will undergo simply tautomerization. After that, it will result in the formation of HC double bond O, then it is CH3. That means this is the aldehyde. Or you can directly use this trick. Have a look. You can directly use this trick. Now we will directly use trick. You have HgSO4 or you have H2SO4 and you have heat. Now what you have to do is break two bonds between carbon-carbon triple bond so that it becomes single bonded carbon. After that, now add oxygen to that carbon which is having what we call lesser number of hydrogens, but both are having same hydrogen, so it's our choice. So I will give double bond oxygen to this, and after that two hydrogen to this, so it will be simply HCO and CH3. That means this is an aldehyde which is formed over here. Now after that, if I write down another reaction, you can directly use trick and tell me the product. You can use trick directly and tell me the products. You can use trick over here and tell me the products. Come on, tell me the products. Come on, tell me the product. This will be, this is very easy reaction. Now, what do you have to do? Break two bonds. That means carbon and carbon will result in the formation of what we call a single bond first. After that, oxygen will form double bond with that carbon-carbon triple bond which is having lesser number of hydrogens. That means this one. And other two hydrogens will be added to that carbon-carbon triple bond which is having more number of hydrogens. That means it results in the formation of a ketone. So this is simply CH3, C double bond O, and then CH3. This is what we call hydration of alkyne, or this is known as Kocharov's reaction. Now, if I write another example like this, what will be the product over here? What will be the product over here? Very easy reaction. Now tell me the product. What will be the product? How you will add water across this carbon-carbon triple bond. This is very easy. What you have to do is, you simply broke these two bonds. After that, this is the trick. After that, form carbon-carbon single bond. Now, among water, oxygen will form a double bond with that carbon-carbon triple bond which is having lesser number of hydrogens. That means this one. And two hydrogens from water will go to that carbon-carbon triple bond which is having more number of hydrogen. I mean to say it's like this. Now, this is what we call a ketone once again. So during this reaction, we cannot obtain formaldehyde. Have a look. The smallest aldehyde which we get is, acetaldehyde, ethanol. Now, second, as we know, it's having at least two carbons. If this H is equal to R and this H is, still there, that means it will result in the formation of what we call, here it will be double bond O and here it will be H. That means ketone will be formed at that time. That means among aldehyde, acetaldehyde will be the only choice which you can obtain with the help of this reaction. After that, it's by hydroboration oxidation of alkynes. Very easy reaction. Now, remember, hydroboration oxidation. During hydroboration oxidation, what was the reagent? Reagent was diborane in presence of THF, and this THF will convert this diborane into borane, and after that, that borane will react, and next it was oxidation by using H2O2 in basic medium. Now, I have already told you that whenever you see these types of reagents, and here alkene or alkyne, you have to add water. Now add water, but now across carbon-carbon triple bond, across carbon-carbon triple bond, according to anti-Markovnikov's rule. Here we have to add water, but according to anti-Markovnikov's rule. Now what was Markovnikov's rule? Negative part will go to this and positive part to this. Now what is now anti-Markovnikov? Negative part will go to this and positive part to this. That means it will result first in the formation of an enol, but remember now OH will go to that carbon-carbon triple bond which is having more number of hydrogens. So it will be like this, and here it will be H. So first of all, enol will be obtained. After that, after this, tautomerization will take place, and it will result in the formation of RCH2, and then it is C double bond O and H. I mean say this is what we call hydroboration oxidation of alkyne. That means indirectly we have to add water across carbon-carbon triple bond. Now, if you are having an alkyne like this, CH3C triple bond CH, and you have to, add water indirectly with the help of hydroboration oxidation, what will be the product? Have a look. It's a very, very, very simple reaction. Now you have to add water across carbon-carbon triple bond. How will you add water across carbon-carbon triple bond? First of all, this, addition is according to anti-Markovnikov's rule. So the negative part of water, because by whenever these types of reagents are there, you have to add water. So addition of water takes place according to anti-Markovnikov. So anti-Markovnikov says that negative part of water, that means OH, goes to that carbon-carbon triple bond which is having more number of hydrogens. So it will be like this, CH3, C, then it is double bond CH. After that, OH will be added to this carbon and H to this carbon. So this is an enol. It will undergo, this is an enol. It will undergo tautomerization, and it will result in the formation of more stable, keto forms. So the product of this reaction is like this. Now, can you say what will be the trick? What will be the trick? Now, simply what you have to do is, in one step, what you have to do is, whenever you have to, perform HBO, hydroboration oxidation reaction, you have to add water. But add oxygen now. Add oxygen. First of all, you break two bonds between carbon-carbon so that it becomes single bond. Now, add oxygen, or oxygen will form a double bond with that carbon-carbon triple bond which is having more number of hydrogen. That means oxygen will form a double bond with that carbon which is having more number of hydrogen. That means to this to this carbon, oxygen will form a double bond. After that, add two hydrogens to other carbon. That means this will be the product. Have a look. This is the product. Similarly, if you are having this, what will be the major product? What will be the major product? Have a look. If you are having a reaction like this, say you have to perform hydroboration oxidation. You have to perform hydroboration oxidation to this. Now, what will we do? What will we do? Because we know we have to add water. We have to add water according to anti-Markovnikov's rule. That means negative part of water will go to that carbon-carbon triple bond which is having more number of hydrogen. But this carbon does not have any hydrogen. This carbon does not have any hydrogen. Then what will we do? Remember, add water. Add water across carbon-carbon triple bond in such a way so that OH goes to less sterically crowded, carbon of carbon-carbon triple bond. Now, you have to add OH from water to that to that carbon of carbon-carbon triple bond which is sterically less crowded. Have a look. This is smaller alkyl group. To this triple bond, this is larger alkyl group. So bulkier the group, more crowded is this carbon. So this is less crowded. So what we have to do, we will add OH to this. So we will simply add OH to this carbon. So this is our major product. Then you have to break one pi bond, OH to this and H to this. This is what we call an enol. Now this enol will undergo tautomerization. This enol will undergo tautomerization and it will result in the formation of more stable keto form. That means CH3, C double bond O, CH2, CH2, CH3 is the major product. So this is the major product. This is the major product. I hope this is clear to everyone. Now let me know in the chats, is this clear? Now let me know in the chats, is this clear? Is this clear? Because this is very important point. Generally, we simply use that water has to be added across carbon-carbon triple bond according to anti-Markovnikov's rule. But here, we cannot use anti-Markovnikov's rule. Then we get confused. That's the reason you have to remember this so that there will be no confusion at all. Now, let me know in the chats, is this clear? Is this clear? Is this clear to everyone? Let me know in the chats, is this clear to everyone? Because this is very important. Let me know in the chats, is this clear to everyone? Come on guys, let me know in the chats. Everyone, please respond everyone. Is this clear to everyone? I want confirmation from everyone there. Yes. Okay, great. And show some josh in the chats as well. Show some josh in the chats as well. Now after that, another reaction is by reductive ozonolysis. We know reductive ozonolysis takes place with the help of a reagent. We know a reagent used here are, it's ozone, number one. And after that, we use second reagent with the help of ozone. This ozonide will be formed, and after that, reductive cleavage will take place by using zinc, or it is, zinc H2O, or what we call dimethyl sulfide, or triphenyl phosphine. I hope this is, clear to you, because this we have already discussed this reaction. Now, after that, what we have to do here is, we have basically reductive ozonolysis, yes, of alkenes. We know alkenes like this. What you have to do is, number one, if reductive ozonolysis take place, then you have to simply break this bond and add oxygen to this and add oxygen to this. It's simply, that means you have to break carbon-carbon double bond and form a double bond with oxygen here, over here, similarly double bond with oxygen over here. So this is what we call ozonolysis. Very simple. Let me show you a few examples so that it's, clear. Now, say for example, we are having CH2 double bond CH2. Similarly, if we are having CH3 single bond CH double bond CH2. Similarly, if we are having CH3 single bond CH double bond CH single bond CH3. Similarly, if we are having a structure like this, a ring is there and double bond is there. Similarly, if we are having CH3, CC, CH3, double bond C, CH3 and CH3. And suppose these alkenes undergo reductive ozonolysis, what will be the product? A very easy reaction. What we have to do is, number one, ozone. Sometimes solvent is also there. Say for example, tetrachloromethane, or what we call CHCl3 chloroform, or CH2Cl2. They are the solvents. And after that, zinc H2O. So inert solvent is used there. Now what will happen? You have to break this bond and give oxygen to this with a double bond. Similarly, oxygen to this with a double bond. That means here we will get CH2O. I mean to say we will get HCH and double bond O. Say formaldehyde is obtained. That too, 2 moles. 2 moles will be obtained. Similarly, give oxygen to this, give oxygen to this. So we will get CH3CHO and HCHO. It's very easy. Similarly, if we if this alkene undergoes ozonolysis, then add oxygen over here, so the product will become CH3C double bond OH. That means acetaldehyde, but 2 moles of acetaldehyde will be obtained. What about this? Here it's already hydrogen, here it's already hydrogen. You can write this in this fashion. You can write in this fashion. Here it's a double bond O now and double bond O now. Or you can write down CHO, CH2, 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 CHO in straight line. Now after that, you have to add oxygen here, oxygen here. Similarly, add oxygen here, add oxygen here. So here we will get acetone, but 2 moles of acetone. I hope this is already clear in what we call hydrocarbons. Now, after that, next is methods of preparation of aldehydes only. Now, first we have studied that methods of preparation of both aldehydes and ketones. Now, these are the reactions with the help of which aldehydes can be prepared only. Number 1 is from acyl chloride, that too by a reaction, very important reaction, Rosenmund's reduction. What is this? Have a look. If you are having acyl chloride or acid chloride, remember whenever this acid chloride or acyl chloride, is treated with hydrogen in presence of a catalyst, that is palladium, after that barium sulfate with small amounts of sulfur or quinoline. That means we have poisoned this palladium. That means the efficiency of rate of adsorption of what we call hydrogen on this catalyst has been decreased. What do you have to do? Simply just remove this Cl. Remove this Cl and put H instead of Cl there. That means you will get aldehyde over here. So this reagent is known as Rosenmund's reagent. This is known as Rosenmund's reagent. You can even instead of Rosenmund's reagent, you can use PDCaCO3. That means plus sulfur or quinoline. That is known as Lindlar's catalyst. You can use Rosenmund's reagent, Rosenmund's catalyst or Lindlar's catalyst, with the help of which you can simply convert this acid chloride, acyl chloride to aldehyde. What we have to do is, we have to simply remove Cl, and instead of that Cl, we have to add hydrogen. That's this. That is what we call Rosenmund's reduction. Now, if you are having CH3COCl, simply these reactions should be studied like this. I mean, say with the help of tricks. No need of mechanism at all. Let me tell you. Now, if you are having this aliphatic acid chloride in presence of Rosenmund's catalyst or in presence of Lindlar's catalyst, this Cl has to be removed, and after that, instead of this Cl, you have to add H. So you will get, I mean, say CH3CHO over here. After that, if I use an aromatic, this acid chloride, and Rosenmund reduction here will give, you have to remove Cl, it will result in the formation of aldehyde only. So this is not the reaction with the help of which we can get ketone. This is the reaction with the help of which we can only and only form aldehyde, that too from acid chloride or acyl chloride in presence of what we call poisoned catalysts like Rosenmund's catalyst or Lindlar's catalyst. I hope this is clear to everyone. But remember, you have to note down one thing, that is, we cannot prepare HCHO, that means formaldehyde cannot be prepared during this reaction. So with the help of Rosenmund reduction, formaldehyde cannot be prepared. So cannot be prepared during this reaction. Since HCOCl, I mean say formyl chloride, from which we can obtain formaldehyde, is unstable at room temperature. As this is unstable at room temperature, so we cannot, I mean say, form formaldehyde with the help of unstable formyl chloride. That's why formaldehyde cannot be obtained during this reaction. Now, guys, let me know, is this clear till now? Thank you very much, truly King of Organ. Thank you, Bio Mentor. Thank you very much for appreciating me. Thanks for your love. God bless you. Now, Let me know in the chats, is everything clear? Is everything clear? Is everything clear? Let me know in the chats, is everything clear? Okay, okay. That's great, that's great. That's great. After this, another reaction is from nitriles and esters. What we have to produce, what we have to prepare, we have to prepare aldehyde. Now, what is nitrile? Nitriles mean cyanides. So, with the help of which reaction we can simply prepare aldehyde from nitriles? Have a look. If nitriles are treated with SnCl2HCl, what will happen? Basically, SnCl2HCl, it will react together and it will result in the formation of SnCl4 and nascent hydrogens. That means hydrogens in atomic form. These nascent hydrogens, basically, actually will be added across carbon-carbon triple bond. That means we have to break one bond and we have to add hydrogen to this, hydrogen to this, I mean to say. So what will be the product? Product will be, first of all, RCH double bond NH. This is known as imine. This is known as imine. And after that, when cyanide is treated with SnCl2HCl, it results first in the formation of SnCl4 and nascent hydrogens. What is nascent hydrogen? Hydrogens present in atomic form. So these nascent hydrogens will now add across carbon-carbon triple bond and will result in the formation of imine. After that, it will undergo hydrolysis. It will undergo hydrolysis. Whether it is H3O positive or it is H2OH positive. So hydrolysis will take place. Now, what will happen with the hydrolysis? Breakdown of these bonds because of water will take place. First, one bond will be broken, H and OH will be added. Another bond is broken, then H and OH will be added. So, we will get RCH. Have a look. CH. Then it is OH and OH. We know at this position, at one carbon, two OH groups are generally unstable. So geminal diol is generally unstable. It will lose water molecule. It will lose water molecule. This is unstable. As it is unstable, so it will not be isolated. It will not be obtained. Then what will form? What will be formed over here? So when it loses water molecule very quickly, it will result in the formation of what we call RCH and double bond O. That means we will get aldehyde. We will get aldehyde. Have a look. So can I say this CN has been converted to CHO? So trick is simply whenever you are having cyanide or nitrile and it's treated with SnCl2HCl, just simply remove this CN and instead of CN add aldehydic functional group. That means cyanide will become converted to aldehyde or nitrile will be converted to, aldehyde. And this reaction with the help of which cyanide is converted to aldehyde is known as, this reaction is known as what we call Stephen's reduction. Stephen's reduction. This reaction is known as Stephen's reduction. And remember, this Stephen's reduction is actually, this is actually partial. It's actually partial reduction of cyanide. It's actually partial reduction of cyanide or partial reduction of nitriles. I hope this is clear that how can we convert this cyanide or nitrile to aldehyde. This is one of the examples of this. After that, you can also use dibyl H. What is dibyl H? Have a look. You can also use dibyl H. So alternatively, you can use dibyl H so that one pi bond will be broken. First of all, imine is obtained. So imine is obtained first of all. Now after this, this will undergo hydrolysis. This will undergo hydrolysis. When hydrolysis take place, first break one bond, add H and OH like this. After that, another bond is broken, add H and OH to this. Once again, RCHOH. Whenever two OH groups are there, attached to one carbon, you have to simply lose water and it will result in the formation of aldehyde. So can I write down like this? Can I write down like this? It's RC triple bond N. In short, whenever diable H, whenever cyanide is treated with diable H followed by hydrolysis, what we have to do? We have to simply replace this cyanide functional group with aldehyde functional group. So this is what we call the reaction. And what is this diable H? What is diable H? Diable H means diisobutyl aluminium hydride. So it's simply like this, diisobutyl aluminium hydride. So this is aluminium hydride, and after this it's like this. It's iso, CH3, CH, CH3, CH2. So isobutyl, diisobutyl aluminium hydride. It can be also written like this, isobutyl, and it's twice then aluminium hydride. So diisobutyl aluminium hydride. So you can convert this cyanide to aldehyde with the help of Stephen's reduction or by using diable H followed by hydrolysis. Now have a look. If you are having a cyanide like this, or you are having a cyanide like this, what will be the product? What will be the product? What will be the product over here? A very, very easy reaction. Either it will be SnCl2HCl, or I mean to say followed by hydrolysis, number one, followed by hydrolysis, or it will be diable H followed by hydrolysis. Followed by hydrolysis. What will be the product? You have to simply remove this cyanide and replace this cyanide with the help of aldehyde functional group. So this will be, I mean to say, the product. And remember, if you are having a structure like this, this is also cyanide. But remember, this diable H can convert alkyne to alkene, but it will never, I mean say, reduce this olefinic double bond. That means it can be specifically used to convert this cyanide to aldehyde. So what will be the product? Product will be CH3, CH, double bond CH, single bond CH2, single bond CH2, and then it will be CHO. That means you have to convert cyanide to aldehyde. Another, I mean to say, so these were the reactions with the help of which we can convert cyanide to aldehyde. Another reaction is you can convert ester. You can convert ester. You can convert ester into aldehyde with the help of diable H as well. So diable H can also convert ester to aldehyde functional group. That means whenever you are having an ester, diable H followed by hydrolysis will convert this ester functional group to aldehydic functional group. For example, an example given in your, I mean say, NCERT text like this, C double bond O, OET. What will be the product? What will be the product? Product will be simply convert this ester to an aldehyde. So the product will be CH3, CH2, and after that it will be CHO. So you can convert ester to aldehyde or cyanide to aldehyde by using diable H followed by hydrolysis, or you can convert nitrile cyanide to aldehyde by using Stephen's reduction. Let me know in the chats. Let me know in the chats quickly. Is this clear to everyone? Let me know in the chats quickly. Let me know in the chats quickly. Is this clear to everyone? Let me know in the chats. Guys, quickly. Let me know in the chats quickly. My dear lovely students, let me know in the chats quickly. Is this clear? Is this clear? I need reply from each and every one there. Come on, come on, come on. You can tell me that is this clear to everyone? Okay, Roshni, clear. Methi, clear. Bhargav, clear. Yes, Ruth, clear. Come on, come on, come on. Aditya, clear. Yeah. Okay. Everyone. Yes, great, great, great. Now, after that, another is from aromatic hydrocarbon by oxidation of methyl benzene. Have a look. If you are having a methyl benzene, I mean say toluene. If this toluene is treated with strong oxidizing agents, you know, strong oxidizing agents are KMnO4, K2Cr2O7, whether hot, whether in presence of acidic medium, or I mean say CrO3 plus H2SO4, I mean say Jones reagent, or CrO3 plus water, that means H2CrO4 and chromic acid, or concentrated HNO3. These are the strong oxidizing agents. Whenever strong oxidizing agents are, I mean say this toluene or methyl benzene is treated with strong oxidizing agents, it will result basically in the formation of benzoic acid, but through formation of benzaldehyde. But remember, this benzaldehyde cannot be isolated over here, because once it's formed, strong oxidizing agents will simply convert this aldehyde, I mean say benzaldehyde, to benzoic acid. But we are basically, the question right now is preparation of aldehyde or preparation of ketone, but here it's what we call preparation of aldehyde. That means we want to stop this reaction at aldehydic stage. For that, you have to use suitable reagents, I mean say suitable oxidizing agents. For example, chromyl chloride. What is chromyl chloride? It is CrO2Cl2. Now what will happen? If you use strong oxidizing agents, carboxylic acid is obtained. But we want, I mean say aromatic aldehyde, or we want to convert this methyl benzene to an aldehyde, so we can use chromyl chloride. Have a look. First of all, if toluene is treated with chromyl chloride, CrO2Cl2, in nonpolar solvent, what will happen? It will first result in the formation of a brown complex or brown chromium complex like this. It will result in the formation of OCrOHCl2. Similarly, OCrOHCl2. A brown chromium complex is formed. Brown chromium complex is formed. After that, it will undergo hydrolysis. Or simply H2O is there. So first of all, what is meant by hydrolysis? Breakdown due to water. This bond will be broken. Add H over here and OH over here. Similarly, this bond is broken. Add H over here, OH over here. Now have a look. This carbon will be attached now to two OH groups, or two OH groups will be present at same what we call carbon. After that, this is unstable. I mean to say, first it will result in this formation of this, but as this is highly unstable, it will lose water molecule. That means this cannot be isolated as this is unstable. That's why what will happen over here? It will lose water molecule. Once it loses water molecule, it will result in the formation of what we call an aromatic aldehyde known as benzaldehyde. So with the help of this, you simply convert methyl benzene to aldehyde, and this oxidation or reaction is known as Itard's oxidation or Itard's reaction. So this is Itard's oxidation, or you can simply write Itard's reaction. So this is what we call Itard's oxidation. After that, here is a question. This question was asked in NEET 2021 or 2021. Now, the question is the intermediate compound X in the following chemical reaction is. That means whenever toluene is treated with chromyl chloride, what is this X? Have a look. Whenever chromyl chloride or toluene is treated with chromyl chloride, it results in the formation of X. What is this X? Whose hydrolysis results in the formation of aldehyde. Because this is not obtained, so you can simply hydrolyze it into aldehyde. So this is what we call X. So what is X? X is CHOCrOHCl2. Have a look. CHOCrOHCl2. OCrOHCl2, but this is twice. That means this is our right answer. This is the option of this question. So NEET 2021. So if you remember reactions very well, then it will take hardly 5 seconds, or I mean say 3 seconds to solve this question. After that, with chromium trioxide, you have to oxidize, I mean say this methyl benzene or toluene with the help of, I mean say chromium oxide or chromium trioxide, that means CrO3 in acetic anhydride. So this is acetic anhydride, CH3CO whole 2 and O. Now what will happen over here? It will first result in the formation of benzylidene. It will result in the formation of benzylidene diacetate. It's like this, COCH3, then it's OCOCH3. So benzylidene diacetate will be obtained. Benzylidene diacetate will be obtained. After this, it will undergo hydrolysis. I mean say you have to hydrolyze this. You have to break this bond, add H over here, OH over here. Similarly, broke this bond, add H over here, OH over here. Now I will write down directly the product. Whenever you are having two OH groups attached to, I mean say one carbon, convert that into C double bond O, because it will lose water. It will lose water. So when water is lost, at that time it's C double bond O, and this H will be there. So benzaldehyde will be obtained with the help of this reaction as well. After that, by side chain halogenation or chlorination followed by hydrolysis, have a look. Whenever you are having methyl benzene, have a look. You have to, I mean to say, treat this with chlorine in presence of light or in presence of heat. Why light? Because this is side chain chlorination. This is what we call free radical substitution reaction or benzylic halogenation, so that this Cl will replace H, so it will result in the formation of CH2Cl. Another Cl will replace another H, another can replace another H, but we have to replace two hydrogens. When we replace two hydrogens, now have a look, it will result in the formation of CH, Cl2 and Cl2. That means this product, benzyl dichloride, will be obtained. We can form benzyl chloride as well. If we replace only one hydrogen, we can replace all the three hydrogens, so that we can get what we call benzo trichloride. But for preparation of benzaldehyde, you have to replace two hydrogens by two chlorines. Now after that, you have to do hydrolysis. When hydrolysis of this takes place, this bond will be broken over here. Here OH will be added instead of this. OH will be added, this bond will be broken, OH will be added. In nutshell, we will get, I mean to say, benzaldehyde. We will get benzaldehyde. So this is the reaction. Now after that, here is the question asked related to this in JEE Mains Feb 2024, 2024. Now question is like this. When toluene is treated with I mean say chlorine in presence of light, side chain chlorination will take place. This will not be the product. A is not this, because side chain chlorination will be the product. Yes, A can be this. A can be this. Okay, A can be this as well. A can be this as well. It depends upon. If we remove one hydrogen, this will be the product. If we remove two hydrogens by two chlorine, this will be the product. Both products are correct. But after that, when you did hydrolysis of that, B. So, you know, just we have studied this reaction right now, that if we replace, I mean say hydrolyze this, it will result in the formation of benzaldehyde. That means both A and B are correct. So this is our correct option. Now the question is here. Here it's only one Cl. If it will hydrolyze, if we will hydrolyze this, then Cl will be removed, OH will be there. That means benzyl alcohol should be the product, but this will not be the product if A is this. After that, if A is this, product should be benzaldehyde. It can never be benzoic acid. Yeah, it can be benzoic acid, but if this is CCl3, but this is CHCl2, so this is not the right option. That means this is incorrect, this is incorrect, this is incorrect. So this is the right option. Now, after that, another is by Gattermann-Koch reaction. Its another name is, you can write down this, Gattermann-Koch aldehyde synthesis as well. Aldehyde synthesis. Or you can write down its another name, that is Gattermann-Koch formylation reaction as well. Okay. Now what is this reaction? It is simply a reaction of benzene with CO, that means carbon monoxide, HCl, AlCl3, and with CuCl, small amounts. Now, what will happen? These will form basically an electrophile, and that electrophile is this one. Or it will undergo, say, resonance. So you can show this as well. So this is the electrophile of the reaction. This electrophile will go to benzene and it will result in the formation of a benzaldehyde. It will result in the formation of a benzaldehyde. So whenever benzene forms benzaldehyde by using COHCl, AlCl3 in presence of CuCl, now it will result in the formation of benzaldehyde. Reaction is known as Gattermann-Koch, Gattermann-Koch aldehyde synthesis or Gattermann-Koch formylation. Okay, Gattermann formylation, it's also known as Gattermann aldehyde synthesis. So this is another reaction. The only difference between these two is aldehyde synthesis. I will show you the difference between these reactions. This was Gattermann-Koch aldehyde synthesis. This is Gattermann aldehyde synthesis. So the only difference is in reagent is like this. Instead of CO, we use HCl in presence of AlCl3, anhydrous. So here electrophile will be Hc and then it will be double bond N with a positive charge. Or you can write down its resonating structure like this, Hc triple bond N with a positive charge. So this is the electrophile. This electrophile goes to the benzene ring. So it will form an imine. It will form an imine. Sometimes in presence of this hydrogen chloride, you can say imine hydrochloride will be obtained. But I will write down imine first of all. Now after that, it will undergo hydrolysis. It will undergo hydrolysis. So break both these bonds, add 2 hydrogens to this and 2 oxygen and hydrogen, say hydroxyl groups to this. So we know 2 OH groups are attached to same carbon. Remove water, we will get benzaldehyde. So this reaction is known as Gattermann formylation or Gattermann aldehyde synthesis, and this is known as Gattermann-Koch. So Koch. So as Gattermann-Koch is there, so CO, Koch. Okay, so this is the resemblance, and this is say Hc and HCl. I hope this is clear till now. Let me know in the chat so that we will move forwards, and another topic will be preparation of ketones only. Let me know in the chats, is this clear till now? Let me know in the chats, is this clear till now? Let me know in the chats, guys. Come on. Be very much sincere. Zubair Wani, thank you very much for replying. Aditya, thank you. Okay, Matthew, thank you. Asiba, great. Roshini, nice. Kanmani, shabash, that's great. Kirthana, good. Aditya, Haritha, good. Srishail, okay. Thank you everyone. Now after that, it's from acyl chloride once again. Once again, you have to prepare ketone from acyl chloride. Remember, when you have to prepare ketone from acyl chloride, you have to treat this acyl chloride with dialkyl cadmium. Can I write down in this fashion, dialkyl cadmium? So to differentiate this R from these R, I will simply put a bar or dash over here so that it will be differentiated. In presence of dry ether, what will happen? What you have to remember, you have to simply remember with the help of trick, you have to remember this. Remove this Cl and Cl. You just remove these Cl with this cadmium, so that CdCl2 will be lost. So this will form a bond with R, this will form a bond with R. So here reaction product will be RC double bond O R prime. That means we will get a ketone plus CdCl2. Very easy reaction. Now let me know in the chats what will be the product over here. If I write down CH3COCl and I will treat it with I mean to say CdR2, dialkyl cadmium in presence of dry ether. So take 2 moles of this, remove CdCl2, yeah, remove Cl from both these, I mean say acid chlorides or acyl chlorides, and form the product. Form the product. Quickly. Let me know in the chats what will be the product. Let me know in the chats what will be the product of first reaction and what will be the product of another reaction. Let me know in the chats what will be the name of the first product and what will be the name of second product. Let me know in the chats quickly. Let me know in the chats quickly. Let me know in the chats quickly. Your focus should be more towards lecture rather than this chatting. Okay, come on. So what will be the product? Product will be CH3, COCH3. CO, say for example this R. So CH3CO from this, CH like this, RCO from this and R dash from this. So CH3CO from this and R from this. Here it will be benzene, that means C6H5 phenyl ring, and CO, that means benzoyl from this, and R from dialkyl cadmium. So this will be the product. I hope this is clear. Now after that, it's another reaction is from nitriles. What is nitrile? And with the help of nitrile, how can we obtain, I mean say ketone? Remember, it's basically reaction with Grignard's reagent. Reaction with Grignard's reagent. Have a look. If we are having Grignard reagent like RMGX, so differentiate these two R. Let me write R prime over here. So this is slight negative and this is having a partial positive. This will act as a nucleophile over here. It will attack this electrophilic part, I mean say of cyanide. So it will result first of all an addition product over here like this. In presence of dry ether, what will happen? Have a look. This R prime, C, instead of triple bond, now it will be a double bond, and here R will form a bond. What is this R? This R is an alkyl, or what we call alkyl group of this Grignard's reagent. Now after that, N is having negative charge. To this negative charge, MgX positive will get attracted. So there will be attraction between these two. First of all, this will be formed, and this is an addition product known as adduct. After this, now have a look. This adduct will simply undergo hydrolysis. It will undergo hydrolysis. First, break 2 bonds over here and add hydrogens over here and OH over here. Now, it will result in the formation of NH3 and it will result in the formation of MgXOH. So leave these, I mean say side products aside. Now what will be the product? Product will be R prime, C and R. To this carbon, 2 OH groups will be attached, and after that we know they are not stable, hence they will result in the formation of R prime COR. Similarly, you can write RMGX and you can write over here like this. Aromatic cyanide. Now what will be the product over here? First of all, we know this is having partial positive, this is partial negative. In Grignard's reagent, this is partial negative, this is partial positive. This negative will act as a nucleophile. It will attack to this electron deficient site. In presence of dry ether, first of all, an adduct is obtained. An adduct will be like this. This will be a phenyl ring. Then C, here R will form a bond with this. Then double bond N having negative charge, and then MgX with a positive charge. After that, hydrolysis will take place. Once hydrolysis will take place, we will break down this bond and will add H over here, and OH will be added over here. So the product will be like this. So this will be another ketone formed over here. So if I replace the value of this R with CH3, CH2, or this CH3, CH2, CH3, I mean say these are very, very easy reactions. You can easily do, I mean say these reactions, or you can easily form the product of these reactions as well. So this is what we call how can we convert nitrile to ketone. But remember, you have to remember this. Let me write down over here. Note, if instead of AR or RCN, HCN is used. HCN is used. Then aldehyde is obtained instead of ketone. Have a look. For example, it's the reaction of Grignard's reagent with HCN. What will happen? This is a partial positive side, partial negative side. This is having partial negative charge. This is having partial positive charge. It will simply attack. Nucleophilic attack will take place. In presence of dry ether, an addition product will be obtained. An addition product will be obtained, and that addition product will be H, C double bond N. This is having negative charge. Here it will be R. Here MgX with a positive charge. After that, simply hydrolysis will take place. Hydrolysis will take place. Break this bond, add 2 hydrogens over here, 2 OH groups over here. So these 2 OH will be converted to C double bond O. So in this fashion, an aldehyde will be obtained. I hope this is clear to everyone. After that, from benzene or substituted benzene by Friedel-Crafts acylation, have a look. If you are having benzene ring and then its Friedel-Crafts acylation takes place. We know Friedel-Crafts acylation takes place by using either acid chloride or acyl chloride or acid anhydride in presence of Lewis acid, say for example AlCl3. Now what will happen? This acyl group will be simply introduced in the benzene ring and it will result in the formation of this ketone. And we know this R can be CH3 or this R can be C6H5. I mean to say, if R is CH3, that means acetyl chloride, RCOCl becomes acetyl chloride. So instead of what we call R, here in this ring, what will be introduced? COCH3 will be introduced, and this CH3CO is known as acetyl, and this acylation reaction becomes at that time acetylation. Similarly, if I write instead of R, if I write C6H5, then RCOCl becomes C6H5COCl. This is known as benzoyl chloride, and reaction at that time becomes benzoylation reaction. So acylation, Friedel-Crafts acylation can be Friedel-Crafts acetylation or it can be Friedel-Crafts benzoylation as well. So the product of this reaction at that time will be benzophenone. It will be benzophenone, or you can write down instead of this C6H5. So this is benzophenone, this is acetophenone. Similarly, if you write reaction of benzene with carbonyl chloride or phosgene, this is also known as phosgene, you have to simply write 2 moles of benzene so that reaction will be balanced, and we will get simply benzophenone over here like this. We will get benzophenone over like this, and after that this H and this H, twice HCl will be lost. So benzophenone will be obtained. So this is what we call a reaction, Friedel-Crafts acylation, with the help of which we can obtain ketone. After that, my dear students, it's chemical reactions of aldehydes and ketones. But before starting this, let me know in the chats, is this clear till now? Is this clear till now? And for you have to understand this reaction, you must be very much focused and you have to listen me very, very, very clearly so that these reactions will be very much clear to each and every one. Let me know in the chats, is this clear to everyone? Let me know in the chats, is this clear to everyone? Let me have a sip of water. Let me know in the chats quickly. Is this clear till now? Okay. Okay, now have a look. Nucleophilic addition reactions, we will simply write NAR for them. These are nucleophilic addition reactions are very characteristic reactions of carbonyl compounds, I mean say aldehydes and ketones. Now what are carbonyl compounds? Compounds which contain C double bond O. They are known as carbonyl compounds. But right now we are talking about aldehydes and ketones. Have a look. Have a look. If this is an aldehyde or a ketone, like this. If I write down an example with the help of which we can understand this reaction. Have a look. This is either an aldehyde or a ketone. Have a look. And let me tell you that as we know, this reaction, this compound is basically a planar species. It's a planar species. It's a planar species. Why? Because its hybridization is sp2. We know this is a planar species. Say for example, this is a plane in which this aldehyde or ketone exists. Now, what will happen? Nucleophile will come, and that nucleophile will try to react with this carbonyl compound. But let me know in the chats, do you know that this carbon is having a partial positive charge and this oxygen is having a partial negative charge because of electronegativity difference? And we know because of electronegativity difference, it becomes slightly positive and this becomes slightly negative. That means this is what we call a planar species. It's a planar species. Now, in chemical bonding, you must be, you might have been studied this one, that is LCAO, linear combination of atomic orbitals. From there, you know, whenever orbitals combine in such a way that positive and positive, that means constructive interference takes place, at that time it results in the formation of an orbital which is like this, which is known as what we call bonding pi orbital. Similarly, this is bonding pi orbital, or this is pi BMO, bonding molecular orbital of which results in the formation of a pi bond. Similarly, when positive will combine with negative, like this, and negative with positive, at that time it results in the formation of pi bond, but that is anti-bonding molecular orbital, and we write down that in this fashion, pi star. It's clear in MOT, molecular orbital theory. Now remember, if this is pi bonding molecular orbital, its anti-bonding molecular orbitals will be like this. Its anti-bonding molecular orbitals will be like this, positive, negative. Similarly, it will be negative and it will be positive. So I want to say that pi bonding and pi anti-bonding molecular orbitals does not lie like sigma bonding and sigma anti-bonding molecular orbital. They lie what we call at 180 degree with respect to each other, but they lie almost perpendicular to each other. Now the question is, here have a look. When nucleophile approach, it will attack to electron deficient carbon of this carbonyl compound, or its HOMO, highest occupied molecular orbital, will simply interact with lowest unoccupied molecular orbital of this carbon, according to molecular orbital theory. Or if you don't know HOMO and LOMO, leave it. This nucleophile will simply attack this carbon of carbonyl group, electron deficient carbon of carbonyl group. Now the question is, from which side? It simply attacks this carbonyl carbon from almost, remember NCERT is written in NCERT, it will attack carbonyl carbon or carbon which is electron deficient of this carbonyl group. Nucleophile will attack to that carbon from the side which is approximately perpendicular to this plane, approximately perpendicular. Now the question is, why approximately perpendicular? Why not perpendicular? Basically, when this comes with electron, this pi bonding molecular orbital, which is having electron repulsions will be there. That's why it will go to its anti-bonding molecular orbital, which is empty. Because bonding molecular orbital forms bond and that's having an electron. Anti-bonding molecular orbital is empty. Now it will attack to anti-bonding molecular orbital. It will attack to, now let me rub this one. It will attack to anti-bonding molecular orbital almost perpendicular almost perpendicular to the plane. Exactly, it's not perpendicular. It forms a sort of obtuse angle, approximately 105 degree. Now it will attack to this. Now let me tell you, when it attacks to this, it can attack from this side, almost perpendicular, or it can attack from this side, almost perpendicular. So if it attacks this side, it will result in the formation of C, then it's Nu, then after that it is this bond, after it's this bond, and then it's having O, having a negative charge. It will result in the formation of this. I hope this is clear. Now this was having sp2 hybridization. Now it will form now an sp3 hybridized carbon, and that too can be chiral. This can be chiral if this and this group all are different. Say for example, this is H and H, this is H and H. At that time it's not chiral. If this is H, this is CH3. And this is what we call OH minus, and this is O minus. All the four groups are different, and this is sp3. At that time, it will become a chiral center. So it can be a chiral center. Now, similarly, it can attack. It can attack. Have a look. Have a look. This nucleophile can attack to this, say, carbon of carbonyl group from, say, that side which is opposite to this. That means it can attack in this fashion. Let me show this with the help of another color. But this attack is not exactly perpendicular, it's almost perpendicular. Now, so nucleophile will attack and it will result in the formation of this one. See, it's Nu. Now, Nu, after that, it is, first of all, let me write down this once again. So this was like this. Okay. Now, here it will result in the formation of this, this, and this. Suppose this is chiral, this is chiral. At that time, if this is a mirror, have a look. Can I say these two are mirror images of each other? That means these are enantiomers of each other. So if center is chiral, at that time enantiomers will be obtained, and that too 50% plus 50%. Both the enantiomers will be present in 1:1 ratio or 50% ratio. This is also what we call sp3 hybridized center. When these, say, enantiomers are present in 50-50 ratio, that means we can get a racemic mixture. But for that, first of all, these must be enantiomers. That means this and this carbon must be chiral center. That means racemization can take place during nucleophilic addition or carbonyl compound or aldehyde or ketone. Now, have a look. This will be an intermediate. This or this will be an intermediate. This is tetrahedral intermediate. So first of all, a tetrahedral intermediate will be obtained. And this, say, tetrahedral intermediate. Now, have a look. Tetrahedral intermediate can form product. So let me write down there, say this one. Let me first of all finish this so that you can see product will be basically enantiomers or racemization can take place in the product. So first of all, let me erase this one. Let me erase this. First of all, let me show first of all the product of this reaction, and after that I will write down that. Now, after that, remember my dear lovely students, have a look. After that, it will simply abstract. It will abstract electrophile. This will abstract electrophile, or this can abstract electrophile. So the product formation will be like this. Have a look. It can result in the formation of this one, O and electrophile. This electrophile can be H positive, it can be anything depending upon the reaction. We will see what will be this, and after that it can be like this, Nu, and here it is OE, then it is this wedge bond and dash bond. Now have a look. These are what we call enantiomers of each other. These are enantiomers of each other, and that too in the ratio of 50% plus 50% enantiomers will be obtained. 50% plus 50% enantiomers will be obtained. 50% plus 50% enantiomers will be obtained, and this whole will be simply a racemic mixture, and hence that process, that reaction during which a racemic mixture is obtained, that means we can simply say racemization can take place during this reaction. But the question is this having chiral center or not? If this does not having any chiral center, there will be no, enantiomer formation, there will be no racemization at all. Now, this is basically the mechanism of this reaction. But remember, this is the mechanism if nucleophile is stronger nucleophile. If nucleophile is weaker nucleophile, this is not the mechanism of that reaction. Now, come on, have a look on different reactions of this. But first of all, let me know in the chats, is this clear to everyone? Let me know in the chats, is this clear to everyone? Let me know in the chats, let me know in the chats. And I will write down over here, this is the slowest step of the reaction, and hence this will be the rate determining step of the reaction. Let me know in the chats, is this clear till now? Is this clear till now? Yes, 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 yes. Good, great. Now have a look, have a look. If we talk about reactivity, if we talk about reactivity between aldehydes and ketones, remember aldehydes are very reactive as compared to ketones, and their reactivity can be explained on the basis of either electronic factor or steric factor. Have a look, have a look. If we talk about an aldehyde, if we talk about an aldehyde, this is an aldehyde, and if we talk about ketone, this is the ketone. Have a look, have a look. Now, this is an electron deficient site where nucleophile has to attack. This is electron deficient site where nucleophile has to attack. Now have a look. Attack of nucleophile is basically rate determining step. So can I say over here, have a look, can I say rate of nucleophilic addition reaction is basically directly proportional to nucleophilicity. It is directly proportional to nucleophilicity of nucleophile. That means strength of the nucleophile. It's directly proportional to that. Have a look. Similarly, can I say rate of nucleophilic addition reaction is directly proportional to electrophilicity of C double bond O, which means if this is more electrophilic, rate of nucleophilic addition will be more. But what is meant by this electrophilicity of this? Remember, that means rate of nucleophilic addition reaction is directly proportional to partial positive charge magnitude, or magnitude of partial positive charge, magnitude of partial positive charge on carbon of C double bond O. That means if this carbon is having more magnitude of positive charge, rate of nucleophilic addition will be more. So can I say that means rate of nucleophilic addition reaction is it's directly proportional to electron withdrawing groups attached to C double bond O. So more the number of electron withdrawing groups attached to this carbon, more will be its magnitude of positive charge. More the magnitude of its positive charge, more will be its electrophilicity. More electrophilicity means more will be the rate of nucleophilic addition reaction. Similarly, rate of nucleophilic addition reaction is inversely proportional to electron donating groups attached to C double bond O. If electron donating groups are attached to C double bond O, those electron donating groups will what we call donate electron towards this carbon, and its positive charge will decrease. If its positive charge is decreased, its electrophilic nature decreases. Electrophilic nature decreases, rate of nucleophilic addition reaction will decrease simply. So these are few points which you have to remember before we move ahead. So these are very, very, very important points. You must remember these things. After that, have a look. I will simply write down these points over here. Have a look, have a look, have a look. Can I say rate of nucleophilic addition reaction is directly proportional to molar concentration of substrate, and our substrate is carbonyl carbon. So can I say it's directly proportional to molar concentration of carbonyl and molar concentration of nucleophile. So by doing this, rate of nucleophilic addition reaction is equal to some constant K, molar concentration of C double bond O and molar concentration of nucleophile. So with the help of these 2 points, we can simply say this, say type of reaction, say nucleophilic addition reaction of carbonyl compound is simply bimolecular and second order. It's a bimolecular as well as a second order reaction. Now, have a look. Finally, we are talking about this reactivity. We are talking about reactivity. And reactivity towards nucleophilic addition reaction is, it's basically aldehyde greater than ketone. And we can explain this with the help of 2 factors. Number 1, electronic factor, and another second one is steric factor. Have a look. If we talk about electronic factor, R will donate its electron. That means here R is electron donating. Here 2R will donate electron because of inductive effect. So can I say this carbonyl is having less electron donating group, this is having more electron donating group. Have a look. More electron donating means rate of nucleophilic addition will be lesser. So its rate will be lesser as compared to this. This is electronic factor. Another factor is steric factor. Have a look. Can I say more alkyl group means more crowding? Or when nucleophile wants to attack this carbon, it feels more crowding over here as compared to this. That means more crowding means this nucleophile will not prefer to attack this carbon as compared to this. So can we say that rate of nucleophilic addition reaction is inversely proportional to steric crowding. Lesser the crowding at carbonyl carbon, more will be the rate of, what we call nucleophilic addition reaction. Now let me know in the chats, is this clear till now? All points are clear, yes or no? Let me know in the chats. Let me know in the chats. Let me know in the chats quickly. Is this clear to each and everyone? Is this clear to each and everyone? Let me know in the chats. Quick. And come on, show some josh as well. Come on, yes, Mathi, yes sir, Kithana, nice beda, clear, very good, Gina Mark, very good, Zubawanil, great, everything is clear. Now, have a look now. So, among aldehydes, aliphatic aldehydes, if I write down HCHO, say formaldehyde, I will write aldehyde other than formaldehyde. Say for example CH3CHO. I will write down CH3CHO. Now, what will be the rate of nucleophilic addition reaction? What will be the rate of nucleophilic addition reaction? We know more the number of plus I groups, or stronger the plus I, stronger the electron donating group, lesser will be the rate of nucleophilic addition. So it will be like this. Or according to steric factor, more bulkier the group attached to, say carbonyl group, lesser will be its what we call reaction. Similarly, among ketones, what will be the rate? What will be the rate of nucleophilic addition reaction? Have a look. As more bulky groups are attached to C double bond O, the rate will be lesser. So more bulky, more crowding at C double bond O, lesser will be the rate of nucleophilic addition reaction. because it becomes very difficult for nucleophile to attack that C double bond O group. No, according to steric factor, this will be the answer. According to what we call electronic factor, this will be the answer, because more stronger what we call electron donating groups will be there, lesser will be the rate. Similarly, among aldehydes and ketones, say aromatic aldehydes and aromatic ketones, what will be the rate of nucleophilic addition reaction? Have a look. But you must know what is meant by aromatic aldehyde. Aromatic aldehyde is that in which CHO group is directly attached to aromatic ring. Similarly, aromatic ketone is that in which C double bond O group is directly attached to, say this aromatic ring on one side at least. So have a look. So order will become once again this. Why? What is the reason? Once again, reason is same. First of all, aldehydes will be always rate of nucleophilic addition reaction in case of aldehydes will be always greater than that of ketones. So aldehyde first, after that among ketones, this shows plus M effect. This shows what we call plus I or hyperconjugation. This shows plus M effect. This shows plus M effect. And we know more stronger electron donating groups will simply decrease rate of reaction. Or we can simply say, instead of this CH3, we write down benzene over here, or phenyl ring is here. So steric crowding will be more over here. So more steric crowding, lesser will be the reaction. Now, after that, what will be the rate over here? This is simple, very simple. First of all, this is formaldehyde. Then it's aldehyde other than formaldehyde. Then it is what we call aromatic aldehyde. Then aliphatic ketones. And after that, aromatic ketones. Very, very, very simple order. Order will be simply aldehydes first, and among aldehydes, formaldehyde first, then aldehyde other than formaldehyde, then aromatic aldehyde, aliphatic ketone, then after that aromatic ketones. I hope this is clear till now. After that, we are having few examples of this. Addition of hydrogen cyanide. Have a look. You are having C double bond O, you are having C double bond O, and you are having HCN. This is a reversible reaction. It will be a reversible reaction, and reaction takes place in basic medium. Why? What will base do? Have a look. Base will simply come, and that will catalyze simply the reaction by abstracting hydrogen from this cyanide, and it will result in the formation of a stronger nucleophile like this. Once nucleophile is stronger, that stronger nucleophile will attack. That stronger nucleophile will attack to this, and it will become like this. So it will be like this. But we know this O minus can form a double bond and CN will be lost. That means this is basically a reversible effect. And after this, this O minus will abstract. It will abstract H from water. It will abstract H from water. That means it will result in the formation of this product. And this is known as cyanohydrin. This is known as cyanohydrin. So this is the actual mechanism. So this, but you simply write down product of this with the help of trick. Have a look. This is having partial positive, partial negative, partial positive, partial negative. Give negative part to positive part to negative part. That means it will become simply, first of all, broke this bond, pi bond, into a single bond, double bond, convert a double bond into single bond. After that, give this negative part of reagent to positive part of this. That means it is CN, and give it to this. It will be like this. Now, the question is, if this is, say for example, CH3 and this is H, that means this is CH3, this is H. At that time, racemization will take place. So, sometimes question will be asked like this: which of the following can undergo racemization? Which of the following can undergo racemization? For example, question is like this: which of the following, which can undergo racemization? Which can undergo racemization during addition of during addition of HCl or during nucleophilic addition reaction. Not necessary only HCl, it can be nucleophilic addition reaction. Say for example like this, CH3 CHO. Number second, CH3 C double bond O, CH3. For example, third one, C double bond O. Fourth one, CH3 CH2 C double bond O, CH2 CH3. Following can undergo racemization. Have a look. You have to check, is this carbon chiral or not? If this carbon is chiral, racemization will take place. But we know in cyanohydrin, OH and CN is already different. That means you have to look towards these groups. That means you have to find out these two groups. If these two groups are different, racemization will take place. Have a look. These two groups are different, hence racemization will take place. These two groups are same, racemization will not take place. These two groups are same, racemization will not take place. This and this group, they are same, hence racemization will not take place. I hope this is clear. After that, next is like this. But before doing this reaction, let me know in the chats, is this clear? Racemization is clear. Which can show racemization or which cannot show racemization? Let me know in the chats. Yes. Exactly. Roshini, nice. First is the right answer. Nandani, exactly. One is the right answer. Methi, yes, sir. Thank you very much for replying. Reply everyone. Roshini, yes. Nandani, yes. Okay. Methi, yes. Clear. Anugya Chaudhary, 100 subscriber. Okay. Now, Kriti, yes, sir. Okay. So, everyone, this is clear. Now, after that, addition of sodium hydrogen sulfide. Sodium hydrogen sulfide is also known as sodium bisulfite. It's also known as sodium bisulfite. Have a look. This is very important chapter as per NEET is concerned. Have a look. Sodium bisulfite means this one, NaHSO3. So it is actually like this. It is Na positive, then it is O having negative charge, then SO2, and then it is H. It is, I mean, say SO3H. It's like this, it's like this, it is like this, it is like this, it is HSO3. So it's like this. Now have a look. If you are having C double bond O and then you are having Na positive, you are having O negative, then S double bond O and OH, which will act as a nucleophile. Common sense, use common sense. Which will act as a nucleophile? Obviously this negative part will attack over this positive part, as this is the electron deficient site. That means this will donate its electron to this and this bond will break. And it will result in the formation of, see, here it will be OSO2H, OSO2H. It will be like this, or I can write down it in this fashion, O, S double bond O and then O and then H. It can be like this. And here it becomes O negative. This Na positive will go to there with the help of attraction. So it will result in the formation of this. But we know this is acid. It will lose H positive. When it loses H positive, this O minus can abstract this H positive. That means after this it is simply proton transfer. It's simply proton transfer which takes place. It's simply proton transfer. It's proton transfer which takes place. Now it will become COH and then it becomes OS double bond O negative and then Na positive. Now, what is the driving force behind this transfer? It becomes more stable and this negative charge is resonance stabilized as well. So this is the reaction. But remember, you have to remember that this O having negative charge and SO2H, this is considered, it's considered bulkier nucleophile. It's considered a bulky nucleophile. Now, if it is a bulky nucleophile, when nucleophile is bulky, it does not prefer crowding at this substrate. That's why this is considered as bulky nucleophile. Hence, all aldehydes show this reaction. All aldehydes show this reaction. Then, aromatic ketones generally do not show this reaction. aromatic ketones like acetophenone, benzophenone, aromatic ketones like acetophenone means this one, PHCOCH3. This is acetophenone. Similarly, benzophenone, PHCOPH, etc. Do not show this reaction. Do not show this reaction. So all aldehydes show this reaction, but aromatic ketones generally do not show this reaction. And among aliphatic ketones, only methyl ketones show this reaction. Methyl ketones, I mean to say, are C double bond O CH3. That means there must be at least one CH3 attached to C double bond O. Among aliphatic ketones, only methyl ketones show this reaction. Why methyl ketones can show this reaction? Because methyl ketones are considered sterically less crowded. When nucleophile is bulky, your carbonyl must be less crowded. It must be either aldehyde or it must be aliphatic ketone. That too, among aliphatic ketone, it must be methyl ketone only, so that this reaction can take place. I hope this is clear to each and every one. After that, another reaction is addition of Grignard's reagent. Have a look. We are having Grignard reagent like RMGX, and we are having C double bond O group. We have already studied this reaction in last session in amine say alcohols. Now have a look. In presence of dry ether, what will be, say, the mechanism of this reaction? Have a look. This negative part of Grignard reagent will act as a nucleophile and it will attack to electron deficient carbon of this substrate. So what will be the product? Product will be an addition product like this. Now have a look. 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 This negative part can form double bond and this CN, a good leaving group, can leave. That's why reaction is reversible. Now have a look. Here negative part can form double bond and this is a good leaving group and it can leave. It can leave. Because this is the conjugate base of H2SO4 and H2SO4 is a stronger acid. Conjugate base of stronger acid is a weak conjugate base and weak bases are good leaving groups. That's why it can leave and it is a reversible reaction. But here, this is either H or carbon. This is simply a carbon. Carbon or hydrogen, they are not good leaving groups. So it cannot form a double bond and reaction cannot be a reversible reaction. It is an irreversible reaction. Remember that. Okay. After that, this is an addition product. Say adduct. Now, after that, we will simply hydrolyze this. That means hydrolysis of this will take place, and after hydrolysis, this bond will be simply broken and give OH to this, say carbon, and H to this. So the product of this reaction will be alcohol like this. Product will be alcohol and side product will be MgX, and with this there will be OH, say hydroxy magnesium halide. Very, very, very simple reaction. In a simple go, you can simply give negative part to this, positive part to this. So this will be the product. Instead of this MgX, OMgX, substitute that OMgX by OH. This will be the final product. Now after that, it's addition of alcohol. Have a look. 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 This is, say, aldehyde or a ketone, but remember aldehydes show this reaction more readily. Ketones generally do not show this reaction readily. After that, you have to add alcohol. I will write down like this. I will write down like this. If alcohol is taken in excess, have a look. If alcohol is taken in excess, just remove water. Just remove water molecule. Just remove what we call a water molecule from there. Just remove water molecule from there and the product will be like this. Have a look. Product will be like C, then it will be OR and it will be OR. That means it will be a geminal dialkoxy compound. Geminal dialkoxy compound. What is meant by alkoxy? RO means alkoxy. Dialkoxy means two alkoxy group are there. Both are present to same carbon. That's why geminal dialkoxy compound. If it is obtained from aldehyde, then it is known as acetal. If it is obtained from ketone, then it is known as ketal. So remember forever, whenever aldehyde or ketone reacts with alcohol, it either results in the formation of acetal or ketone. But most of the times, it is aldehyde which give acetal. Ketals are generally not formed with the help of this reaction, because ketones are little, once they form ketal is very unstable in case of ketone. That's why they prefer to remain in ketonic stage. And as this nucleophile, ROH, is a weaker nucleophile, and this reaction takes place only if alcohol is taken in excess. And this is a weaker nucleophile. Weaker nucleophile never attacks directly. It takes place, reaction takes place in presence of acid. Reaction takes place in presence of acid. Why? Because, have a look. What will this acid do? It will basically simply gets protonated. This ketone or aldehyde gets protonated. It gets protonated, with the help of which oxygen becomes O positive. Once oxygen becomes positively charged, it simply increases the electrophilic nature of this carbon. Have a look. Because when oxygen becomes positive charge, it abstracts it or attracts electrons of carbon towards itself, and it increases positive charge of this carbon. That means it increases electrophilic nature of this carbon. Once electrophilic nature of this carbon is increased, then weaker nucleophile can attack and reaction will proceed. Now have a look. This reaction can be shown like this. If we write down this reaction in this fashion, C double bond O plus it is ROH. It's a reversible reaction, but as alcohol is a weaker nucleophile, whenever weaker nucleophile is present, at that time reaction takes place in presence of acid. Now this acid simply increases the rate of nucleophilic addition reaction. Now what will happen? This is slight positive charge, this is slight negative charge, this is negatively charged, and this is positively charged. Give negative part to positive part and positive part to negative part, you will simply form this one. It will result in the formation of this. This is what we call monoalkoxy compound. This is known as hemiacetal. This is known as hemiacetal if this is an aldehyde. So generally this reaction is shown by aldehydes, so this is hemiacetal. After that, if further alcohol, excess of alcohol is used actually, so ROH in presence of acid is used, what will happen? This negative part will simply, negative part of alcohol, that means OR, will replace this OH. It will replace this OH. Have a look. It will replace this OH. Now, and it will result in a formation of geminal dialkoxy compound obtained from aldehyde, and this is known as acetal. Now, this OH will first, what we call abstract H positive from acid, becomes OH2 positive, a good leaving group that will leave. That means water can be formed. So what is the function of acid over here? One, it increases the electrophilic nature of this aldehyde or a ketone, generally aldehyde. Second, the water formed here, it simply will simply react with that water and it will remove that water, because if water is there, reaction will go back to aldehyde. That's why HCl or acid is used. Now similarly, if we use an aldehyde or a ketone, you can use a dihydric alcohol, say for example ethylene glycol, and this ethylene glycol can result in the formation of a cyclic acetal or cyclic ketal, depending upon aldehyde or ketone, depending upon whether the starting material is aldehyde or starting material is ketone. Have a look. Now, it will result in the formation of PTS is taken as a solvent and then reflux. PTS means para-toluene sulfonic acid. Now, so here product will be like this. It is OCH2 it's once again OCH2, but they will result in the formation of a ring. So cyclic acetal or cyclic ketal will be formed. Why ketones can show this reaction? Why ketones do not generally prefer reaction with monohydric alcohols? Here ketals are not that much stable, but here because of this ring, I mean say chelate effect, ketals are also stable. So this is the reaction with monohydric alcohol. After that, a very important reaction. This is not written in NCERT, but this is very important reaction, and that is addition of water. Now have a look. If you are having C double bond O and water is added, water is a very weak nucleophile, I mean say it's a weak nucleophile. So whenever weak nucleophile is there, reaction takes place in presence of acid, so that this acid can simply increase electrophilic nature of carbonyl compound. After that, have a look. It will result in the formation of OH and OH, because negative part of water goes to this positive part and positive part of water goes to this. It's like that. But this is known as geminal diol. Geminal diol, or it is simply geminal glycol, or we can simply call it as hydrate. We know this is generally unstable. Generally unstable. Because of this repulsion, it will lose water molecule and will form into aldehyde or ketone back. But there are few, remember, there are few aldehydes or ketones. But before that, have a look. But before that, you must know, if you are having an alkene like this, if you are having an alkene like this, which alkene is more stable and why? Which alkene is more stable and why? Which alkene among these is more stable and why? Which alkene is more stable among them and why? Let me know in the chats quickly. Which alkene is more stable among these and why? The order of stability will be like this, because this is not having any alpha hydrogen, this is having 3 alpha hydrogens, this is having 3 and 3 6 alpha hydrogens, and this is having 3 3 6 9 12 alpha hydrogens. So more the number of alpha hydrogens, more will be the stability. Similarly, my dear lovely students, similarly, if you are having a carbonyl compound like this, so remember, more the number of alpha hydrogens, more will be simply stability, or more donating the groups, more will be the stability. Now tell me, which carbonyl is least stable? This is least stable carbonyl compound. After that, this is more stable, and this is most stable. So this is stability order. So can I simply say stability order of C double bond O group, stability order of C double bond O is directly proportional to electron donating groups attached to C double bond O. Remember, and stability of C double bond O, stability of C double bond O, stability of C double bond O is inversely proportional to electron withdrawing groups attached to C double bond O. I hope this is clear to each and every one. This is very important point. Now have a look. C double bond O is very stable if electron donating groups are attached, and it is unstable if electron withdrawing groups are attached. Have a look. If you are having HCHO, can you say it's highly unstable, or it is least stable among aldehydes? Least stable means it's very reactive. It's very reactive. That's why it can react. It can react with water. It can react with water. It can react with water to form, I mean to say, HCH, OH and OH. And remember, its hydrate is approximately 99.9%. That means this formaldehyde prefers to form what we call hydrate, or it prefers forward direction. It prefers to stay at hydrate stage, because in this stage it is highly unstable or it's least stable. Similarly, if I write down like this, if I write down like this, this is known as CCl3, trichloroacetaldehyde, commonly known as chloral. Trichloroacetaldehyde, commonly known as chloral. Now, have a look. Can I say this CCl3 group is electron withdrawing? This is electron withdrawing. Electron withdrawing group destabilizes, I mean say, carbonyl compound. So this is less stable. As this is less stable, it is very reactive. As it is very reactive, it prefers to react with H positive. When it prefers to react with H positive, so let me show you like this, it prefers to stay in its hydrate stage. That's why equilibrium will shift towards, I mean say, forward direction. So its hydrate will be formed easily. So it will form its hydrate like this, Cl, 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 and then it is simply this H is there. After that, it's having OH, or let me write down this H over here. It's having O and H. So it prefers to be present in its hydrate form. Why? As this is least stable. And second, as we know here, it is electrostatic force of attraction between this electropositive and electronegative chlorine. Similarly, this is having negative, this is having positive. So electrostatic force of attraction between this positive charge and negative charge will also stabilize this. But the reason is basically this is unstable. That's why it prefers, the equilibrium shifts towards forward direction. Plus, this is more favorable because of this attraction as well. Similarly, instead of CCl3, if I write CF3, have a look. If I write CF3, once again, it is simply an electron withdrawing group. It becomes unstable and it will react with water, and it prefers, or it simply helps to move equilibrium in forward direction. It helps to move equilibrium in forward direction. Why it helps this reaction in forward direction? Because this is less stable or unstable because of electron withdrawing group. Because of presence of electron withdrawing group, this is very reactive. Plus, another factor will favor that. Have a look which factor will favor it. It's simply C, then it is CF, F and F is there, and after that it is O, to which you have to add H, and another carbon you have to add OH. Here it will be what we call electrostatic force of attraction once again between H and F, but this attraction, we can simply call this attraction as what we call hydrogen bonding. So here intramolecular hydrogen bonding also prefers to shift equilibrium towards right. But actually, why equilibrium shifts from this to this side? It is actually, this is least stable. Similarly, if you have a look, if you are having this one, this is known as indane 1, 2, 3 trione. Now tell me, among these, as we are having more than one C double bond O group, now the question is which C double bond O is more reactive, and the question is why, or to which C double bond O water will simply add. Have a look. This C double bond O is stabilized because of resonance. That means these two are stable due to resonance, but this is not stable due to resonance. This is unstable because of this electron withdrawing group. This is unstable because of electron withdrawing group. So this positive and negative, water will attack positive, say negative part of water will attack to here and positive part will go here. So it will result in the formation of this. It will result in the formation of this. It will result in the formation of this. Have a look. This is double bond O, this is double bond O, and after that it is O, to which H is here, and one OH will be here. Let me show you in this fashion. It is OH and it is OH. Have a look. As this is less stable because of electron withdrawing group, this C double bond O is less stable. This C double bond O is less stable because of electron withdrawing groups. Hence, highly unstable will prefer to move towards forward direction. That's why equilibrium shifts towards this direction. Plus, this is what we call hydrogen bonding over here. Hydrogen bonding will also help to move equilibrium towards right direction. This is known as ninhydrin. This is ninhydrin. So these are few, these are few examples. 1, 2, let me write down. This is 1, this is 2nd, this is 3rd, this is 4, whose hydrates are stable. And another example, last example, example number 5, whose hydrates are stable is cyclopropanone. It's a ketone, cyclopropanone. Have a look. You know, this is sp2 hybridized carbon. Its angle should be 120. So this is expected angle. This is expected angle. But its actual angle is 60 degree. Its actual angle is 60 degree. So there is deviation from expected angle, and that deviation is 60 degree. Due to that deviation, it is having angle strain. It's having angle strain. But once we add what we call water to this, we add water to this in presence of H positive. Why H positive? Because water is not a good leaving group. It will result in the formation of this one. It will result in the formation of this one. It's O. To that O, it will be attached to H, and another O should be attached to H. First of all, now it's having an angle strain. This is now what we call sp3 hybridized. This is sp3 hybridized. Its expected angle should be what we call 109 degree 28 minutes or 109.5 degree. Its actual angle is 60 degree, because we know cyclopropane is having inner angle of 60 degree. So deviation is only 49 approximately. Here deviation was 60 degree. So more deviation, more strain, less deviation, less strain. That's why it prefers towards less strain. That means more stable state. So that's why few aldehydes or ketones will prefer, say hydrated stage. Otherwise, generally, they will prefer to go in equilibrium, will shift towards backward direction in general aldehydes and ketones. But these were few examples where equilibrium shift towards forward direction. Let me know in the chats, is this clear till now? After that, and another reaction is what we call nucleophilic addition reaction followed by elimination of water molecule. But before that, let me know in the chats, is everything clear till now? Is everything clear till now? Let me know in the chats quickly. Let me know in the chats quickly. Let me know in the chats quickly. Roshni, yes sir. Thank you beta for replying. Nice. Mathi, yes sir, clear. Great. Thank you beta for replying. Aditya, yes sir. Okay, Roshni, yes, it's clear sir. Momin Billah, sir, looking really good. God bless you. Thank you beta. Okay, Kuri Minion, okay. Please let me know in the chats, is everything clear? Yes sir, clear. Okay, yes. Saha, yes sir. Okay, yes sir. Okay, thank you. God bless you. Now, have a look. This is basically nucleophilic addition reaction followed by elimination of water molecule, but it's actually addition of ammonia and its derivatives. Let me tell you, ammonia is this one. It's NH2 and H. This is ammonia and its derivatives. That means if this H is removed or replaced by some other group, say for example that group is represented by Z. So what is this Z? Z can be H. Z can be any group. Say for example, it can be, say it can be R. Now, if this is R, at that time it's primary amine. It can be OH. If it is OH, then it is hydroxylamine. It can be NH2. When it is NH2, it's hydrazine. It can be NHPH, then it's phenylhydrazine. Then it can be NH, and then phenyl ring should be attached to this. To that phenyl nitro group should be present to 2 and 4. That means it can be 2,4, say dinitrophenylhydrazine. Okay, I mean say it can be semicarbazide. I mean to say different values of Z can be used. But these all are weaker nucleophiles. Whenever weaker nucleophiles are there, reaction takes place generally in acidic medium, and its pH is approximately 3.5. Now, what will happen? This nucleophile will first of all attack to this C according to this mechanism. Have a look. First of all, H positive will react with this so as to increase its electrophilic nature. After that, this nucleophile will attack. Nucleophile attacks. It will result in the formation of this. Then proton will be lost from this, and that proton will be abstracted from this abstracted by O. That means here will be simply proton transfer, and it will result in the formation of this. Now, as we know, this becomes good leaving group. This is a good leaving group now. It will lose, and this can form a double bond over here. Finally, H positive, which was first used, will be lost. That means it can act simply as a catalyst, and it will result in the formation of C double bond N single bond Z. But first of all, nucleophile will be added. After that, water will be lost. That means first it is nucleophilic addition followed by elimination of water molecule. And the intermediate is this one. This is the intermediate. When nucleophile is added, first it will will form this, and after that this water will be lost. That means elimination will take place, and product will be this. Now, what is basically the reaction? Have a look. Reaction is actually this one. You have to remove 2 hydrogens from nitrogen, and you have to remove oxygen, and after that carbon and nitrogen will form a double bond. So this will be the product. Now have a look. These are few different examples written in your NCERT textbook. Now I have written it so that we can simply save our time. Now, if value of Z is H, that means it's ammonia. If value of Z is R, it is amine. If value of Z is OH, it's hydroxylamine, NH2OH. Now what you have to do, whatever the value of Z is, you have to simply put that over here. Suppose first put H over here, write down the products, it will be C double bond NH. Whenever C double bond NH is the product, it's imine. Similarly, when it is C double bond NR, it's substituted imine known as Schiff's base. So these are few examples which I have written already over here. But remember, this is 2,4-DNP, 2,4-dinitrophenylhydrazine, also known as Brady's reagent. And when it forms 2,4-dinitrophenylhydrazine, its color is generally yellow, orange, or red. For that purpose, we can simply use this DNP. Remember, we can use 2,4-DNP, 2,4-dinitrophenylhydrazine, or Brady's reagent to differentiate. Aldehydes or ketones or formic acid, as formic acid is also having this group, sort of it resembles like that of an aldehyde. That's why formic acid can also show this reaction. So aldehyde can show this reaction, ketone can show this reaction, this formic acid can show this reaction. So we can use 2,4-DNP to differentiate these compounds from rest of the compounds, which do not show this test. Say for example, if you are having an aldehyde or a carboxylic acid, you have a doubt between an aldehyde and a carboxylic acid, say for example acetic acid or ethanoic acid. You have doubt that my test tube contains either an aldehyde or ethanoic acid. You just add 2,4-DNP to it. If yellow or orange or red coloration takes place, it is an aldehyde. If yellow, orange or red color is not obtained, then it is ethanoic acid. That means those compounds, for example aldehydes, ketones or formic acid, we show this test can form yellow, orange or red color. Other compounds which do not show this reaction, they do not show yellow, orange or red color. With the help of this test, we can distinguish other compounds from aldehydes, ketones or formic acid. So you have to remember this, what will be the product. But here you have to remember like this. In case of this, I mean say semicarbazide, in case of semicarbazide, what is the formula for semicarbazide? It will be NH2, then NH, then CO, then NH2. That means you are having two NH2 groups. But that NH2 which is attached to NH can attack as a nucleophile. That NH2 which is attached to C double bond O cannot act as a nucleophile, because it takes part in resonance. But that NH2 which is attached to this NH will act as a nucleophile. Remember that. And that N which acts as a nucleophile, you have to remove two hydrogens from that. So this is the only thing you have to remember, otherwise it's all clear to you. Now, here one question is given regarding to this in NEET 2022. What was the question? Question was, you have to match this to this. Now have a look. Product is, these are the products, and this is reaction of carbonyl compound. Reaction of carbonyl compound with NH4OH. Reaction of carbonyl compound with NH4OH. Have a look. It's basically, it's not actually NH4OH, it is NH2OH. A reaction of carbonyl compound to NH2OH. Have a look. Have a look. A reaction of carbonyl compound to NH2OH. NH2OH is known as hydroxylamine. That means Z is having OH, hydroxylamine. What will be the product? C double bond NOH. That means oxime will be the product. Have a look. Have a look. So it will simply, this will form oxime. Oxime is this D. That means D is the product when this is the reactant. That means D and 1, they are one and the same. After that, it's primary amine. Have a look. Have a look. If this is primary amine, that means NH2 and R. That means value of the Z is R. Value of Z is R. It's primary amine. At that time, it forms substituted imine. That means Schiff's base. Have a look. It will result in the formation of Schiff's base, and that is C. That means C is the product of second reaction. I hope this is clear to you. Then alcohol. When alcohol reacts with, say carbonyl compound, you have already seen that it results in the formation of acetal. That means this third is basically the reactant of this product, acetal. After that, HCN, it will result in the formation of cyanohydrin. That means A is the product of 4. A is the product of 4. That means only first choice is there. So this is not the answer, this is not the answer, this is not the answer. We simply write down first is the answer. But if we want check, then A4, then B3, then C2, then C2, and after that it's D1, it's D1. So done and dusted. This question is simply explained less than 20 seconds. Okay. After that, it's a reduction. Number one, it's a reduction. Reduction of what? Either aldehyde or ketone to alcohols. We know. It's simple. It's simple. It's like this. You have to reduce aldehyde to alcohol by this. You have to break one bond, add hydrogen to this, and add hydrogen to this. That means you will result in the formation of this. You will result in the formation of this. And if it is aldehyde, say if it is aldehyde, it will always result in the formation of primary alcohol at that time. We have already, studied this reaction in alcohols. If it is ketone, at that time, it will result in the formation of what we call a secondary alcohol. Now, the question is, what are the reducing agents? Let me write down once again those reducing agents which we have already studied in alcohols. Number one was, lithium aluminium hydride, with or without water. Number second, it's sodium borohydride, with or without water. Number third, what's meant by that, with or without water? If water is not given, take water as solvent. So water is always there. Number third is sodium in alcohol. And number four is hydrogen in presence of catalyst, whether that catalyst is platinum or palladium or nickel. So these are the reducing agents which will simply convert alcohol, aldehydes or ketones to alcohols. After that, next is reduction to hydrocarbon. We know there are three, reactions with the help of which you can convert hydrocarbon, aldehyde or ketone to hydrocarbon. Number one is Clemmensen reduction. Detail of this reaction, if you want to see this reaction in detail, you can see hydrocarbons. Now, this is, C double bond O. After that, Clemmensen reduction, zinc amalgam in acidic medium. What you have to do, just replace this, remove this hydrogen, this oxygen by 2 hydrogens. So this is the reaction. Similarly, in this, you have to remove this oxygen, but in basic medium, say for example hydrazine, NH2 or N2H4 in basic medium, say for example KOH, and generally ethylene glycol is the solvent, that is the high boiling solvent, but it's not necessary that ethylene glycol is written there. So NH2, N2H4, hydrazine OH minus and high temperature. Now it will result in the formation of CH2 plus N2 gas will be evolved. After that, it is a reaction with HI, red phosphorus. A very simple reaction. That means you are having an aldehyde or a ketone plus HI in presence of red phosphorus. Just remove oxygen, and instead of that, you have to add hydrogen. It will result in the formation of this one. So this is the reaction. After that, we are having oxidation of aldehydes or ketones. Have a look. We know in case of aldehyde, if we want to oxidize aldehyde, we have to break this bond. We have to break CH bond. But in case of ketones, we have to break CC bond. In case of ketones, we have to break CC bond. That's why upon oxidation, remember, upon oxidation, CH bond is weaker, CC bond is stronger. So this oxidation takes place easily. This oxidation shows resistance. Ketones show resistance towards oxidation because of a cleavage of strong CC bond. But it can undergo oxidation easily. That's why it takes place either by using strong oxidizing agents or by using mild oxidizing agents. It takes place only by using strong oxidizing agent, and that too under drastic conditions. Not normal conditions. Under normal conditions, there will be no oxidation of ketone. So under drastic conditions. Have a look. We have already studied these reactions. Now, oxidation of aldehyde by using strong oxidizing agents. Now, whenever you are having aldehyde, RCHO, what you have to do is, under the influence of strong oxidizing agent, what you have to do is that simply you have to add OH instead of H. That means convert simply CHO group into COOH group. That's it. Convert CHO group into COOH group by using strong oxidizing agents. Now the question is strong oxidizing agents. What are strong oxidizing agents? Let me write down over here. Strong oxidizing agents generally used are either KMnO4 in neutral, alkaline or acidic medium. Number one. Number second, it's K2Cr2O7 in acidic medium. Say for example H2SO4. Number third, it can be KMnO4 hot, or it can be K2Cr2O7, hot K2Cr2O7. Remember, these are considered as strong oxidizing agents. So whenever I write strong oxidizing agent, that means among these some oxidizing agents have been used. After that, number 5, it is CrO3 plus H2O. say aqueous chromium trioxide. This is known as what we call H2CrO4. This is known as chromic acid. Number 5, it is CrO3 plus H2SO4. That means it is Jones reagent. It's Jones reagent. Or simply we can use HNO3 concentrated. Generally concentrated, sometimes dilute HNO3 can also be used. So this is the reaction. We have already studied this reaction in what we call alcohols. because from alcohols we get first aldehyde and after that we get carboxylic acid. Similarly, this is now from aldehyde to carboxylic acid. After that, it's oxidation of aldehyde by using mild oxidizing agents like Ag positive and Cu di positive. Ag positive came from basically Toland's reagent and Cu di positive came from either Fehling solution or Benedict solution. So that means we are basically reducing these Toland's reagent, because Toland's reagent will oxidize aldehyde. That means in turn it will get reduced by itself. Have a look. Say for example, silver nitrate is there. We take silver nitrate in one test tube and to that we add ammonium hydroxide solution. When we add this to this, it will result first in the formation of gray precipitate of Ag2O, but we continue add ammonium hydroxide till this gray precipitate redissolve. First form, then redissolves and it becomes a clear solution, and that clear solution is known as Toland's reagent. After that, this Toland's reagent is added to aldehyde and little heat. We will heat this solution a little bit, and after that silver will be deposited along the walls of the test tube and it will start shining like that of a silver or like that of a mirror. That's why this is known as silver mirror. That's why this is known as silver mirror, because it now shines like that of a mirror. I mean to say, whenever AgNO3 silver nitrate reacts with ammonium hydroxide, first it will result in the formation of these two. When results in the formation of gray precipitate of Ag2O, its gray precipitate will be obtained. Now, in addition to this, ammonium nitrate will be formed. Ammonium nitrate will be formed plus H2O will be obtained. Have a look. 2 oxygens, 8 oxygens, 1, 2 and 6. Yes, reaction is balanced. After that, this Ag2O, we have to add further ammonium hydroxide to this till this Ag2O precipitate is dissolved. Now, it will result in the clear solution, and that clear solution is basically Toland's reagent. So, what is Toland's reagent? It's ammonical silver nitrate solution. So, this is Toland's reagent. This is Toland's reagent, and this is a coordination complex. It will result in the formation of a positively charged species. This coordination complex, complex positive charge, and a simple anion will be formed. After that, Ag, it will be 2, then ammonia, it will be 4, yes, oxygen 4 and 1, 5. That means 3 times water will be there. So reaction will be balanced. So this is Toland's reagent, freshly prepared Toland's reagent. Once it is formed, it reacts with an aldehyde. Whether aldehyde is aromatic, whether aldehyde is aliphatic, it should be an aldehyde. To that, we use Toland's reagent. Have a look. But from Toland's reagent, I need 2 cations. I need 2 cations and 3 anions. From one Toland's reagent, 1 cation, 1 anion will be formed, and from many molecules, it will be many cation, many anion. But I need 2 cation and 3 anions so that reaction can be balanced. So it will simply oxidize this RCHO into RCOO negative. That means addition of oxygen has been taken place. So this is oxidized. This Ag positive acts as an oxidizing agent and it will get reduced in Ag0 oxidation state, and this will now shine like of a mirror. That's why this is silver mirror. Plus 4 times ammonia will be there. Now we have to check oxygen. 3 oxygen, 4 oxygen. 2 oxygens are there, that means twice water. So this is the reaction basically. What will happen? This Ag, that means Toland's reagent, is reduced and this aldehyde is oxidized. Which type of aldehyde shows this reaction? It is basically aliphatic as well as aromatic aldehyde. That means all types of aldehyde show this reaction. All types of aldehydes show this reaction. One more thing I want to say over here is glucose. This is very important point. Glucose do not show. Glucose does not show. 2,4-DNP test. 2,4-DNP test. Remember this as well. Glucose is having CHO group, but glucose generally exists in its cyclic form. That's why it cannot show 2,4-DNP test. Okay. Now here all types of aldehydes, here all types of aldehydes show this reaction. All types of aldehydes show this reaction. Now, let me write down which types of amine say compounds can show this reaction. All aldehydes show this reaction. All aldehydes. Number one. Number second, ketones do not show this reaction, but alpha hydroxy ketones can show this reaction. Alpha hydroxy ketones can show this reaction. Number third, formic acid can show this reaction. Number four, pH NHOH, phenyl hydroxylamine, can show this reaction. Number five, hemiacetals can show this reaction. Number six, terminal alkynes. I have already write down this one, this reaction in hydrocarbons, in acidic nature of alkyne. Terminal alkynes can show this reaction. But here, white precipitate will be obtained. White precipitate will be obtained. And in these five cases, silver mirror will be obtained. So we can distinguish, I mean say aldehydes from rest of the ketones, otherwise this, I mean say otherwise apart from alpha hydroxy ketones, but aldehydes can be distinguished from ketones as well, but apart from this. Similarly, we can distinguish alpha hydroxy ketone from rest of the ketones. This will show silver mirror test, that will not show silver mirror, those will not show silver mirror test. Similarly, formic acid from rest of the compounds. Similarly, this. So these are the compounds which can show this test, otherwise rest will not show Tollens test or silver mirror test. This is very, very important reaction. Now, okay, one question was asked from NEET 2023 from this. Identify the major product obtained in the following reaction. So these are the cations and anions which are from Tollens reagent. I mean say, now this is an aldehyde group. Have a look. This is an aldehyde group. It will be simply oxidized, but this is a ketonic group, and ketonic groups are not oxidized. Only one ketone, that is alpha hydroxy ketone, but this is not alpha hydroxy ketone, so this cannot be oxidized. So it will oxidize this CHO to CO minus, and it will remain as it is. Now, which of the following is the correct answer? This is the correct answer, because it remain as it is. Ketone will remain as it is, CHO gets oxidized to CO minus. So in less than, I mean say 2-3 seconds, you can answer the question as well. After that, reduction of Fehling solution. Now the first question is Fehling solution. What is meant by Fehling solution? Tollens solution was ammonical silver nitrate solution. So the question is, what is Fehling solution? Fehling solution is actually alkaline solution of what we call copper sulfate containing some Rochel's salt. Rochel's salt means sorry, sodium potassium tartrate. Have a look. We are having basically two Fehling solutions. One is Fehling solution A, another is Fehling solution B. It was asked somewhere in NEET. I will show you the question. I don't know exactly in NEET 2022, 23, 24. I don't know exactly, but it was asked. Fehling solution A is, it is aqueous solution of copper sulfate, not alkaline. It's aqueous solution of copper sulfate, and Fehling solution B is alkaline solution of what we call Rochelle salt. Rochelle salt means sodium, alkaline solution of sodium potassium tartarate. Sodium potassium tartarate. Remember this forever. Okay. Now we will add first Fehling solution B to Fehling solution A. Little bit, and we will stir the, I mean say test tube, and there will be a precipitate formation of CuOH2. Why? Because Cu dye positive from this and OH from this alkaline solution will combine and result in the formation of cupric hydroxide. It will be a blue precipitate. After that, we will add further Fehling solution B till this precipitate is dissolves, and there will be a blue color solution, clear blue color solution known as Fehling solution. So what is Fehling solution? It is simply alkaline solution. Alkaline solution of copper sulfate containing some Rochelle salt. Have a look. What will happen actually? if you are having an aliphatic aldehyde, not aromatic aldehyde, only aliphatic aldehyde show this reaction. Now, if you are among aldehydes, only aliphatic aldehyde show this reaction. If you are having this, you will simply write down Cu di positive from this solution, it will react, and OH minus from Fehling solution will react. So, these will come from, say, Fehling solution. Now, what will be the reaction? It is basically this RCHO which gets oxidized into RCO minus, and among Fehling solution it is Cu2 positive which gets, say, reduced to Cu1 positive, and it will precipitate in the form of a red precipitate. After that, it's 2, 3, 6, that means 3 times H2O. Reaction is balanced. Now, have a look. Cu di positive is converted to Cu1 positive, that means it is reduced, that means it is reduction of Fehling solution, but oxidation of what we call aldehyde. Now, the question is, which aldehydes show this reaction? Remember, it is, say, aliphatic aldehyde, to say aromatic aldehyde. Aromatic aldehydes and ketones do not show this reaction. Do not show this reaction. That means this reaction can be used as a test. Do not show this reaction. This reaction can be used as a test to distinguish aliphatic aldehyde from aromatic aldehyde. Similarly, aliphatic aldehyde from ketones, or we can simply distinguish these types of aldehydes. Number one, aliphatic aldehyde, remember, aliphatic aldehyde, it shows the reaction. Number second, formic acid, it shows the reaction. And alpha hydroxyketone shows the reaction. So these types of compounds shows the reaction. So we can distinguish these types of compounds from rest of the compounds with the help of this red precipitate or red color, say with the help of Fehling solution or Fehling solution test. Now, the question was asked in 2024 that Fehling solution A, it's not Fehling solution, it's not Fehling solution B, it's Fehling solution A. Fehling solution A is aqueous alkaline solution of sodium potassium tartrate. No, this is what we call Fehling solution B. Aqueous sodium citrate. No, aqueous copper sulfate and aqueous alkaline copper sulfate. It is aqueous copper sulfate. So in less than 3 seconds you can answer the question. Okay, after that, it's a Benedict solution. Remember, it's same as that of Fehling solution. Reaction, say reaction is same. Reaction is same as that of Fehling solution. What is the difference? Have a look. In case of Fehling solution, we have Cu di positive ions complexed with tartarate ions, and in case of Benedict solution, we have Cu di positive ions complexed with citrate ions. So this is the only difference, that here it will be a citrate ion, and in case of say Fehling solution, it was tartrate ion. Reaction will be same. Reaction will be once again like this. RCHO twice Cu positive 5 times OH, but these will now came from Benedict solution instead of Fehling solution. Reaction will be once again same. After that, we are having another, that's Schiff's reagent. Remember, first of all, if you are having Schiff's dye, say aqueous solution of rosenolin hydrochloride. Remember, this is very, very important. Its color is pink. It's having pink color. When you pass sulfur dioxide, to this pink colors, say dye, it will result in the formation of Schiff's reagent, and its color is lost. That means it becomes colorless. But once they are treated, I mean say once this Schiff's reagent is treated with aldehyde, its pink color is restored. Its pink color is restored. Its pink color is restored. Say for example, if we want to distinguish aldehyde from ketone, suppose I have a doubt whether this test tube contains an aldehyde or a ketone, I will simply first of all add SO2, I mean say pass SO2 gas through Schiff's dye, it becomes colorless, that means Schiff's reagent. I will add Schiff's reagent to this. If it remain colorless, then this is ketone, that means ketones do not respond to this test. But if this colorless Schiff's reagent becomes colored, pink color is restored, that means compound in this test tube is aldehyde. So remember, ketones do not respond to this test. Ketones do not respond. Ketones do not respond to this test. I hope this is clear. But remember one more thing, that means aliphatic aldehydes are more reactive as compared to, I mean say aromatic aldehydes over here. After that, it's oxidation of ketones by using strong oxidizing agents. Now, remember ketones generally show resistance towards oxidation. But under drastic conditions, following reactions take place. Following reactions take place. Now, have a look. Say for example, you are having a ketone, symmetrical ketone like this, CH3, C double bond O and CH3. I will simply write down strong oxidizing agent over here and I will tell you the trick. Just break one carbon, I mean say one bond between one alkyl group and C double bond O. Now the question is, should I break this bond or this bond, as they are, I mean say same, so you can break this or that, anyone. After that, it becomes two fragments will be formed. One will be 2 carbon fragment, another will be 1 carbon fragment. So convert this 2 carbon fragment into acid and convert this 1 carbon fragment into acid. So one acid will be 2 carbon fragment acid, that means this one. Another will be 1 carbon acid fragment, that means this one. But remember, this HCOH is always, I mean say further oxidized in presence of strong oxidizing agent, and it will result in the formation of carbon dioxide and water. That means product of this reaction is CH3COH, carbon dioxide and water. But if you are having an unsymmetrical ketone like this, or you are having symmetrical ketone like this, first of all, what will happen in presence of strong oxidizing agent? You have to break this bond, convert this into carboxylic acid and this also into carboxylic acid. This is having 3 carbon fragments, so 3 carbon acid will be formed like this, CH3CH2COH, and this is having 2 carbon fragment, that means 2 carbon acid will be formed like this. This is a very easy reaction. But whenever you are having an unsymmetrical ketone, cleavage is done, I mean say cleavage is done in such a way so that cleavage is done according to Popoff's rule. And what is Popoff's rule? We have already written that in, I mean say alcohols, but let me tell you once again. Popoff's rule says that C double bond O group stays with smaller alkyl group. This is smaller alkyl group and this is larger alkyl group. So C double bond O group stays with smaller alkyl. That means C double bond O and large alkyl group, the bond between larger alkyl group and C double bond O is broken. That means it becomes 2 carbon fragment, which means 2 carbon acid will be obtained. So this is, I mean say, oxidation of ketones by using strong oxidizing agents, but this takes place only in presence of under drastic conditions. After that, it's another reaction, that is oxidation of aldehyde and ketones by using sodium hypohalite. What is meant by sodium hypohalite? It means NaOX. It's also like this, X2 plus NaOH. Sometimes we can use bleaching powder as well, CaOCl2 plus water. Take, we can use KOH as well. Now, the question is, what is this reaction known as? This is known as haloform reaction, or this is simply halogenation of aldehydes and ketones in presence of base. Now, the question is, which types of aldehydes or ketones can show this reaction? Remember, these types of aldehydes or ketones can show the reaction which contains this group. That means only those aldehydes can show this reaction which is having this group. Yani among aldehydes, there is only one aldehyde. Among aldehyde, there is only one aldehyde which can show this reaction, and that is CH3CHO, known as ethanol or acetaldehyde. Other aldehydes will not show this reaction. And among ketones, only methyl ketones will show this reaction. Only methyl ketones will show this reaction. What is meant by methyl ketones? That means there must be at least one CH3 group on one side of, say, ketone. So, for example, you are having this one. So, this can show. If you are having this one, this will show haloform reaction. If you are having this one, it will not show haloform reaction. Have a look. Why? Because there must be, this is known as alpha carbon, because this is the functional group, at least there must be one CH3 group attached to C double bond O. So this will not show the reaction, this will show the reaction, this will show the reaction. Now, if we want to complete the reaction of this, what is the trick? Have a look. You have to remember it's X2 and NaOH, or this is NaOX, or it is KOX, or it is X2 in presence of NaOH, or it's bleaching powder. Okay, now this is, to say, what will be the trick? Have a look. You have to simply remove or break bond of CH3 at alpha, one of the CH3 at alpha and C double bond O. Similarly, one of the CH3 here, two CH3 are at alpha position, but one CH3 you have to broke with, say, C double bond O. Convert this CH3 into CHX3. Convert CH3 into CHX3. This is very, very easy trick. You have to convert CH3 into CHX3, and after that, this C double bond O, add ONA to this. Add ONA to this. Now tell me what will be the product? HCOONA. That means another product will be HCOONA. Here, what will be the another product? CH3COONA. That means CH3COONA. Now, the question is, if halogen is iodine, then it will be CHI3, and that is iodoform, and the color of iodoform is yellow. So, yellow precipitate will be obtained. This is known as iodoform test. Now, have a look. So, which type, which can form iodoform test? Which types of compounds can show iodoform test? We have already studied in case of alcohols, which type of alcohols will show. Let me write down once again. These types of alcohols can show iodoform test. These types of alcohols can show iodoform test. Can I say these types of halogen can also show iodoform test? Why? Because this reaction takes place in presence of base, which is having OH minus. That OH minus will attack this, and it will replace X. That means it can form CHOH. If CHOH is formed, then it will form iodoform test. Similarly, it can be shown by this type of aldehyde. It can be shown by this type of compound as well. Remember, these all compounds can show iodoform test or haloform, what we call reaction. All can show haloform reaction or iodoform reaction, or simply iodoform test. All can show. These can show iodoform test. Why? Have a look. This is the mechanism. Actually, base will come and abstract proton, forms a carbanion. That carbanion will attack halogen, and there will be one halogen instead of one H. Similarly, 3 times reaction will take place. So 3 hydrogens will be replaced by 3X. After that, it becomes CX3. Now, this cannot abstract hydrogen because there is no alpha hydrogen. Now it will act as a nucleophile, not as a base. It will attack over here. Pi bond will be broken, then it will be formed, and CX3 minus is a good leaving group. It will leave. So it becomes an acid and it becomes CH3 having negative charge. Acid loses H positive and this will abstract H positive. In nutshell, proton transfer will form, proton transfer will take place and iodoform or chloroform or bromoform. In nutshell, CHX3 will be formed and it will form sodium salt of carboxylic acid. That's why I have simply written over here a trick. That means CH3 is converted to CH3, but CH3 should be at alpha position, that position which is directly attached to C double bond O of aldehyde or ketone. And number second, this C double bond O is having should be attached, O and A should be attached to this. This is the trick. Now the question is, have a look. It's not having any halogen, but if one halogen is already present as CH2X, so reaction will proceed from that and it will also form. If it's having two halogens at alpha positions, iodoform or chloroform or haloform will be formed. If it's having 3X at alpha, then this reaction can also be obtained. So that's why these, without, CH2 having 1X at alpha position, have a look, alpha, alpha, this is alpha, this is alpha. Either CH3 should be present at alpha or CH2X, CHX2, CHX in case of aldehydes or ketones can show. Similarly, if it is having what we call halogen, if it is having halogen at this position, sorry, these are alpha in among aldehydes and ketones, we have to check alpha CH3, alpha CH2X, alpha CHX2 or alpha CHX or alpha CX3, or these types of compounds can also show iodoform test. I hope this is clear to everyone. Now after that, CH3CHO, have a look. This is alpha, this is alpha. Now both are aldehydes, but both are aliphatic aldehydes. So we cannot use Benedict's test because both can show Benedict's test. We cannot use Toland's test because both can show Toland's test. We cannot use Falling's test because both can show Falling's test. So with the help of which test we can distinguish them? This is having CH3, C double bond O group, but this is not having CH3 at alpha position. Hence we can distinguish these two types of aldehydes with the help of iodoform test. This was asked in AMPMT 2012. Very easy question. After that, reactions due to alpha hydrogen, very important reaction known as aldol condensation. This is the most important reaction because many times questions were asked from this question, this aldol condensation. But before starting aldol condensation, let me know in the chats, is everything clear till now? Is everything clear till now? Let me know in the chats quickly. Let me know in the chats quickly, and I will have a sip of water as well. Quickly, let me know in the chats. Let me know in the chats. Roshini, Ruxana, Methi, good. Shabash, come on. I've already told you in the beginning of the session that this session will end from 3:30 hours to, say 4:30 hours. So between 3.5 hours to 4.5 hours, this will be finished. And this is very important. Thank you so much, sir, for standing and teaching us for such a long time just for our learning. God bless you, my dear student. God bless you. It's my duty. So no need to thank me, but I will thank you if you will be sincere through whole session. Okay. Now after this, this is a very important reaction and known as aldol. Condensation. Give me 1 minute. Okay. Now what is aldol condensation? Have a look. First of all, if you are having an aldehyde, say for example CH3CHO, have a look. First of all, I will simply write down like this. Reaction in which aldol, that means beta hydroxy aldehyde or ketol. I mean to say beta hydroxy ketone is obtained from aldehydes or ketones having at least one alpha hydrogen. Generally it is one acidic hydrogen. Is called aldol reaction. By using mild bases, or dilute bases like NaOH dilute or 10% NaOH, or it may be KOH as well, or BaOH whole 2 dilute, I mean say, or it can be CaOH whole 2 dilute, or it can be aqueous Na2CO3. So any type of base can be used, and if we are having an aldehyde containing at least one acidic hydrogen or one alpha hydrogen, and from those aldehydes or ketone having at least one alpha hydrogen, so if we are having aldehyde or ketone having at least one alpha hydrogen, and in presence of these mild bases we get what we call aldol or ketol, then we call that reaction as aldol reaction. Similarly, reaction in which alpha beta unsaturated aldehyde or alpha beta unsaturated ketone is obtained from aldehydes or ketones containing at least two alpha hydrogens, and both must be acidic, remember that, in presence of mild bases or in presence of dilute bases or mild bases, is called aldol condensation. So it's clear that for aldol condensation we must have an aldehyde containing at least two alpha hydrogens, and for aldol reaction we must have an aldehyde or a ketone containing at least one alpha hydrogen. But here aldehyde or ketone must contain at least what we call two acidic hydrogens, must contain at least two acidic or two alpha hydrogens. I mean say, this aldol condensation or aldol reaction is basically of two types. It is acid catalyzed, and another one is base catalyzed. But our focus should be on base catalyzed, because whenever we are having aldol condensation in our syllabus, that is base catalyzed. So not needed, acid catalyzed is not needed. Now we are having aldol condensation or aldol reaction, that will be base catalyzed, and this is of two types. One is known as intermolecular, that means between the molecules. Another is intramolecular, that means within the same molecule. Have a look. This intermolecular is further of two types. One is self or simple. That means between the molecules, and those molecules must be same types, same type of molecules. Now, or another is mixed or crossed. That means here molecules are of different types. So, first of all, we will start this self or simple intermolecular base catalyzed aldol condensation. After that, we will see mixed intermolecular base catalyzed aldol condensation, and after that intramolecular aldol condensation. Now, have a look. So, let us start with self. Let's start with self aldol or simple aldol condensation. Have a look. Now, if I write CH3CHO, have a look. Now, tell me, is this aldehyde having any alpha hydrogen? Yes. At least there must be one alpha hydrogen for aldol reaction, and at least there must be two alpha hydrogens for aldol condensation. Now, if this is treated with OH having a negative charge, remember what will happen over here, and if same substrate is treated with OH having negative charge, and after that it's having heat, what will be the product? Now, have a look. First of all, it's not written how many moles of CH3CHO is there, but it's written only one type of aldehyde is there. When only one type of aldehyde is there and you are having a base OH minus, or you are having BaOH whole 2 OH minus is there, you are having CaOH whole 2 OH minus is there, you are having KOH OH minus is there, you are having NaOH OH minus is there, you are having Na2CO3 aqueous. Remember, they can also, and Na2CO3 plus water can also form NaOH, that means OH minus is there as base. Now, what you have to do is, have a look. You have to first of all think like this. You have to think like this. It is CH3, then it is C double bond O and H, and write down another same type of molecule by itself. But first of all, you write down one molecule like this and show positive part and negative part of C double bond O. Then write another molecule, but in such a way so that one alpha hydrogen will be shown at alpha carbon like this, C single bond H. Other hydrogens in combined form. After that, it is C double bond O and H. Now, what you have to do when OH minus is there, if this is the reagent, then you have to write down the product of aldol reaction. That means you have to write down product of aldol reaction, means you have to form beta hydroxyaldehyde, as this is an aldehyde. If this was ketone, then you have to find out ketol, that means you have to find product of aldol reaction, that means you have to form beta hydroxyketone. Here, product should be of aldol condensation. Here, product will be aldol condensation. That means whenever aldehyde or ketone is treated with OH minus, it's aldol reaction. When aldehyde or ketone is treated with OH minus and heat, it is aldol condensation. Remember this. Now, first of all, I will show this one without heat. What will happen? Have a look. Have a look. This is the trick. This is alpha carbon having partial negative charge, because carbon is more electronegative as compared to hydrogen having partial positive charge. Now, simply join this negative with this positive and this positive with this negative and break this carbon double bond O into single bond. So, first of all, I will break carbon double bond O into single bond O. After that, this positive part goes to this negative part, that means O becomes OH. After that, this alpha should attach, as it's having negative charge, this is having positive charge, join these two. That means I will join alpha carbon to this carbonyl carbon, and this will be the product of the reaction. And this is main functional group, so this is alpha, this is beta, so this is having beta hydroxyaldehyde. This is beta hydroxyaldehyde, commonly known as what we call aldol. So, beta hydroxyaldehyde product is formed from aldehydes, and both these aldehydes are same type. This is acetaldehyde. So, whenever both aldehydes or both ketones are same and they are treated with base, they result in the formation of aldol. Reaction is known as aldol reaction. But here, if this aldol is heated, have a look. If this aldol is heated now, what will happen? As medium is basic, so I will heat this, medium is basic. Now what will happen? Hydrogen from alpha and OH from beta position will lose, and it will result in the formation of water. But in basic medium, H positive base will come and it will abstract H positive from alpha carbon easily, and it will form a conjugate base of this because it removes H positive. Anything which donates H positive is acid. So it donates H positive from alpha position, it forms a carbanion. That means it forms a conjugate base. But OH minus is not a good leaving group. It will leave after some time. So there will be a double bond between alpha and beta carbon. So the product of this reaction will be alpha beta unsaturated aldehyde. So this is the product of this reaction, alpha beta unsaturated aldehyde. Unsaturated aldehyde. But I have already written over here that product alpha beta unsaturated aldehyde, alpha beta unsaturated aldehyde, or alpha beta unsaturated ketone is the product of aldol condensation. That means this to this is aldol reaction, from this to this is aldol condensation. So remember forever. This is, from this to this is aldol reaction. This is aldol reaction. This is aldol reaction. But if I write down like this, if I write down like this, that means this whole reaction from this to this is aldol condensation. So what is the difference between aldol reaction and aldol condensation? If we start with aldehyde, final product of aldol reaction will be aldol beta hydroxyaldehyde, but final product of what we call aldol condensation will be alpha beta unsaturated aldehyde. Number second point is that aldehyde must contain one acidic or one alpha hydrogen for aldol reaction, but it must contain at least two alpha hydrogens for what we call this aldol condensation. Second, aldol reaction plus dehydration, because water has been lost. So aldol reaction plus dehydration of aldol, both are combined together, and that reaction is known as aldol condensation. So aldol condensation is nothing but aldol condensation is first aldol reaction and then dehydration of aldol. But remember, as this dehydration takes place in basic medium, because medium was basic, this is an example of E1CB. That means conjugate base unimolecular elimination. That means it is that elimination reaction which takes place via formation of conjugate base. So I hope this is clear till now. Now, have a look. So this was the trick formation of aldol. Once again, I will show, write down this. If you are having now CH3, C double bond O, CH3, and reaction is like this. Reaction is like this. In presence of base, and another reaction is in presence of base and heat. In presence of base and then it is heat. Say it's like this. So here product of the reaction should be, such that, so reaction will be known as aldol reaction. So this reaction is aldol reaction, but this is known as aldol condensation. Now I will show you now trick of aldol reaction and aldol condensation. Have a look. You have to write down first of all aldehyde or a ketone in this fashion and form positive and negative part at carbonyl compound. Number second, you have to write now same type of ketone, because this is simple or self condensation, but you have to show one hydrogen like this at alpha position. So alpha becomes partial negative, this becomes partial positive. So for aldol reaction, what is the trick? Have a look. Trick is simply that this positive part goes to this negative part, this negative part will form bond with this positive part. But first of all, you have to simply convert double bond into single bond. Now this CH3, this side I will write down like this. Now after that, this H goes to this. Why? Because this was having positive part, this is having negative part, so it's like this. After that, this alpha will form bond with this, because negative will form bond with positive part, and it will be like this. CH2, after that CO, then it is CH3. So our functional group is now ketone. This is alpha, this is beta. So this is beta hydroxy ketone. This is beta hydroxy ketone. And this beta hydroxy ketone here is known as ketol. But reaction is still known as aldol reaction, because aldol or ketol, basically ketol resembles like that of say aldol. So that's why we simply call formation of ketol or formation of aldol reaction as aldol reaction. Now, if this is heated, there will be a double bond between alpha and beta, and water will lost. So this is aldol reaction trick. Now, what is the trick for aldol condensation? Have a look. Trick for aldol condensation is just write down one C double bond over here. Similarly, show another like this. At alpha position, show like this. Two hydrogens from this side, and then it is like this. But this trick is only applicable if there is condensation. How can we say that there is condensation if heat is also there? Now, what will happen? Now have a look, have a look. Simply oxygen from this and two hydrogen from this, water will be lost. There will be water which will be lost. So water will be lost. What will happen? This carbon can form now a double bond with this. So that's why it will become like this. CH3C, CH3, double bond, CH, single bond, C double bond, O, single bond, CH3. So this is alpha, because this is main functional group, alpha beta unsaturated ketone. Whether it is alpha beta unsaturated aldehyde or alpha beta unsaturated ketone, this is simply what we call aldol condensation. I hope this is clear to each and every one. Now let me know in the chats, is this clear? Is everything clear till now? Let me know in the chats, is everything clear till now? Let me know in the chats quickly. Let me know in the chats quickly, is everything clear till now? Let me know in the chats, let me know in the chats quickly. Everyone, shabash, come on. Unaishi, yes. Mathi, yes. Kanmani, good. Everyone, yes. Jacqueline, good, great. Everything is clear. Now, the question is how these types of reactions take place, whether it is aldol reaction or it is aldol condensation. That means the mechanism for this reaction will be. Have a look. Very important reaction. Very important reaction. Have a look. First of all, if you are having an aldehyde or a ketone having at least one alpha hydrogen, what will happen? In presence of base will come and it will abstract hydrogen from alpha position, and it will result in the formation of a carbanion or enolate ion. It will result in the formation of a carbanion or enolate ion. What is meant by that? Have a look. Water will be lost, and it will result in the formation of CH2 having negative charge, then C double bond O, and then H. You know, the resonating structure of this will be like this. It will be like this. So it will be CH2, double bond C, single bond O having negative charge, and then it is H. So this is known as enolate ion. So first step is formation of enolate ion. That means abstraction of base from say alpha position. Why from alpha position? Because this hydrogen is acidic, because after removal of this hydrogen, you can see this carbanion or this negative charge is resonance stabilized. As it is stable, so it can lose H positive, so it's acidic hydrogen. And this step is slowest step, or hence we can say rate determining step of the reaction. Now after that, attack of nucleophile or attack of this enolate ion. This enolate ion, whether you write down like this or you can write down like this. But attack, remember, attack will be always from carbon. It will not from this, because if this attacks this carbon, it will be oxygen-carbon bond, which is not stable. It will simply like this. It will form this and then this will attack. Either you will simply attack from this or you will attack directly from this. Choice is yours. Now, after that, what will happen? What will happen, my dear students? Have a look. It's simply nucleophile which will attack to this. That means it is nucleophilic addition reaction. Second step is nucleophilic addition reaction. Now, what will be the product? It will become CH3, then it is CH, then it becomes O having a negative charge. Now, to this C, CH2 forms a bond. But when this CH2 forms bond, double bond gets converted into single bond. That means it is CH. And then it is double bond over here. So anion is obtained. After that, when this anion is obtained, CH3, CH having a negative charge, CH2, CHO, it will now simply abstract hydrogen from water. It will abstract hydrogen from water like this, and product formation takes place. So it will result in the formation of CH3, CHOH, then it is CH2, then it is C double bond O, and then H. So this is beta hydroxy aldehyde. I mean say aldol will be obtained. So aldol will be obtained if you simply start reaction with, say aldehyde with at least one alpha acidic hydrogen. This OH will be lost. This OH will be lost. So I mean to say OH minus, say base first used and then lost. That means it acts as a catalyst simple. So this is the mechanism of the reaction. Rate depends on, say first step. That means formation of enolate ion. Now, so after that, you don't need now any type of mechanism. So if I will give you a reaction like this, okay. After that, if you are having an aldol, what will happen? Have a look. Now, after that, this dehydration of aldol can take place, but at high temperature. Have a look. This is, can I write CH2 like this, CHH. After that, it is C double bond O and H. Remember, my dear lovely students, what will happen? This OH minus is there, base is there, and at high temperature, this OH minus will attack another hydrogen at alpha position. But this step will take place only if there is another hydrogen already present in aldehyde. That's why aldol condensation needs at least 2 alpha hydrogens. So what will happen? Water will lose and it will result in the formation of CH3CH OH. OH is not a good leaving group, so it will first result in the formation of a conjugate base like this, and after that it will simply, okay, here water will be lost. After that, what will happen? That CH3 CHOH CH minus C double bond OH will simply form a double bond over here. It will form a double bond over here and OH minus will be lost. That means it will be lost, but it's not a good leaving group. So it will result in the formation of CH3, CH, double bond CH, single bond C, double bond O and H. So this is what we call alpha beta unsaturated aldehyde. This is alpha beta unsaturated aldehyde. But this is the mechanism. You have to understand mechanism once, but you can solve the question with the help of trick. For example, have a look. And this reaction, as it goes via formation of carbanion, this is known as even CB reaction. Have a look. If you are having CH3, CH2, then C double bond O and H, and I want product of aldol reaction, I want product of what we call aldol condensation. Now what will be the product? Now, as only one type of aldehyde is there, you have to remember whenever base is there, it is aldol reaction, and whenever heat is also there, it's aldol condensation. So here reaction will be aldol reaction, and here reaction will be aldol condensation. Have a look, my dear lovely students. Now, what you will do, you will simply write down these reactions twice. I mean, say these aldehydes twice, but in such a way so that first aldehyde you have to show positive and negative, and from second aldehyde you have to show one hydrogen at alpha position. But alpha is this one. That means it is CH2. Then after that it is C double bond OH, because this is at alpha position. Now you have to show another CH3 group because CH3 is also there. So this is CH3. Write down like this. So this is alpha. Now what will you do? This is negative, this is positive. Break this double bond into single bond first. So in presence of OH minus, what will you write down? You will write down CH3, CH2, CHOH. And after that, this alpha will form bond with this carbonyl compound. That means it becomes CH, and after that it is CH3, and then it is C double bond OH. Now, reaction will stop over here. But if this is heated, then form a double bond between alpha and beta position by removing hydrogen at alpha and OH at beta position. So this is trick of this reaction. This is aldol reaction. Now, if you are having aldol condensation, then what will you do? It's simply like this: CH3, CH2, C double bond O, and then H. Another will be like this: H2C, then it is CH3, then it is C double bond OH. Very, very easy reaction is there. OH minus and heat. You have to remove water. Remove water like this. So 2 alpha hydrogens and 1 oxygen. It will result in the formation of CH3, CH2, then it is CH double bond, CH double bond. After that it is C, then it is CH3, and then it is what we call C double bond O and H. So this is what we call aldol reaction as well as aldol condensation. Now the question is, sometimes your product is given. You have to find out the reactants. Have a look. That means that is retroaldol. You have to go reverse in reverse direction. Have a look. This is C double bond O. This is C double bond O. To C double bond O, carbon present in this was alpha. That means this is alpha of the starting material. Then broke this bond, give 2 hydrogens to alpha and give double bond O to another. That means you have to broke this bond, give 2 alpha hydrogens to this, and give double bond O to this. Have a look. Same product, I mean say same reactants were at present at starting material, from which the starting material was like that. You have to broke this, give hydrogens, 2 hydrogens to this, and give double bond O to this. That means you can write down starting material from the final product as well. That is known as retroaldol. After that, another reaction is cross aldol condensation. Cross aldol condensation. Have a look. This is very, very, very important reaction. Now, what we have to do in cross aldol? Have a look. Say for example, you are having CH3CHO and you are having CH3CH2CHO. What you have to do? What you have to do is, have a look, whether you have to show aldol reaction or whether you have to show aldol condensation. What will you show? These types of reactions. Very, very, very easy. Have a look. First of first of all. Now have a look. Is this having alpha hydrogen? Answer is yes. Is this having alpha hydrogen? Answer is yes. If it's having only one alpha hydrogen, that means 4 products will be formed in aldol reaction. If it is having at least 2 alpha hydrogen, 4 products will be formed in aldol condensation. Now the question is, how can we say that 4 products can be formed? Number one product will be like this. A reaction will take place between 2 molecules of this. That means it will be simply self-aldol reaction. It will be self-aldol reaction. Now have a look. Alpha hydrogen from this goes to oxygen and double bond is formed. I mean, say a double bond from this is formed in the form of a single bond. So we can simply write down the product. It is CH3CHOH. Then what was the trick? It's CH2, because H goes there and then it is C double bond O. So this is self product. I hope you can form this. So I will simply remove this. So one is the self product. One is the self product of this. Another will be, have a look, self product of this, CH3, CH2, CHO. I will show in this fashion. This is alpha and here it was CH3, so it is H. After that, it is like this, CH3, this one is alpha, so I will write down H and then CHO. Once again, as both are similar, so self-condensation. So 2 products will be formed. Now third will be CH3CHO. CH3CHO, that means this one, and CH3, I mean say CH2, CH3 and CHO. That means this will be a mixed product. Have a look. Hydrogen, you have to remove hydrogen from this and give it to this. 4th product, you will write down this one, CH3, CH2, CHO. And now remove hydrogen from this one. That means it can be like this. So this is alpha, this is alpha. So this can be another mixed product. So give this H to this, give H to this O, give this H to this O, give H to this O, and then combine alpha and carbonyl, you can form 4 products over here. So this is, I mean say, trick for aldol reaction. So 4 products will be formed. 4 products will be formed. Similarly, my dear students, 4 products will be formed over here. Now the question is how? Remove 2 hydrogens from this and oxygen from this, form a double bond. 2 hydrogen from this, from alpha position, and oxygen from this, form a double bond. 2 alpha hydrogen from this alpha carbon and oxygen from this carbonyl carbon forms a double bond. So 4 products will be formed. Among these 4, which one will be the major product? That is the question. Remember, major product. This is very, very, very important. Major product will be always like this. One will be your least reactive carbonyl compound towards NAR, and another will be basically, remember, another will be more reactive carbonyl compound. That means one should be least reactive, another should be more reactive. That means major product will be always when 2 different carbonyl compounds react. That means it will always, major product will be always from mixed, not from cell, because these both are having same reactivity. These are having same reactivity, but major product should be one least reactive, another will be more reactive. Now have a look. We know, we have already seen, I mean say, nucleophilic addition reaction. We know when electron donating group, strong electron donating group is attached to carbonyl compound, that is least reactive. Have a look. This is CH2CH3 showing more, I mean say, electron donating nature as compared to CH3. So this is least reactive, this is more reactive. This is more reactive, this is least reactive. Here H should be removed from least reactive. That means you have to remove H from this least reactive, and after that it forms enolate ion. Form enolate ion from least reactive, and then it will attack to most reactive. So this will form enolate ion and will attack to this. That means from these two, product will be major product. That means this will be the major product. So from least reactive, you have to remove H and form enolate ion, and after that, that enolate ion will attack most reactive. That means that carbonyl compound which is most reactive, that means to which less electron donating or weak electron donating group is attached, forms, say the major product. I hope this is clear to each and every one. Now, have a look. Have a look. If you are having like this, if you are having like this, if you are having like this, one is C double bond OH, another is having, or let me write down like this. This is very, very, very important reaction. That's why I am giving much more time to this reaction. Have a look. If you are having this one, this aldehyde does not have any alpha hydrogen, but at the very same time, this is having one alpha hydrogen. This is having at least one alpha hydrogen. Have a look. Now, if I will say, go and do a reaction in presence of base, there is no heat. There is no heat. What should be our product? What should be our product? Now, have a look. This is partial positive, this is partial negative, this is partial negative, this is partial positive. First of all, you have to convert double bond into single bond. First of all, convert double bond into single bond and give this H to this O. That means it becomes OH. After that, form bond, single bond between alpha carbon and carbonyl. That means it will form like this, CH2 and then CHO. This is alpha, this is beta. Now, have a look. Have a look towards this aldol. Can I say this is aldol? Alpha, beta, this is beta hydroxyaldehyde, so this is aldol. Whenever your aldol or ketol is having double bond, remember, whenever your aldol or ketol is having double bond at gamma position, at that time it will, by default, it will lose water molecule. By default, it will lose water molecule. Just a moment, as light goes over here. So let me save some, say power supply. Now, am I clear now? Am I clear now? Am I clear now? Let me know in the chats. Am I clear now? So there will be something a little bit darkness, but this will help us. Now, whenever you are having aldol or ketol having double bond or a pi bond at gamma position, by default lose water molecule whether heat is there or not. If there will be no heat, so there will be no aldol reaction, it will be aldol condensation. Now the question is, why is it so? Why, sir? Why? You told us that whenever there is whenever there is heat, at that time you have to form alpha beta unsaturated aldehyde or alpha beta unsaturated ketone. Now, why you are saying that reaction between these two gives us this product, not this product? This cannot be isolated, this will be the final product. Why? Because of extended conjugation. Have a look. This gamma is having pi bond, then alpha beta becomes double bond. Here it's double bond, so extended conjugation. So because of extended conjugation, product will be aldol condensation, not aldol. So simply, whenever you are having a reaction between two different aldehydes, or two different ketones, or one aldehyde, one ketone, between two different carbonyl compounds, and after that, remember my dear students, whenever you are having like this, at that time, whether a reaction takes place between two aldehydes or between an aldehyde or a ketone, then you have to simply, in presence of base, you have to form what we call aldol condensation product if your what we call aldol can form such aldol which contains at least pi bond at gamma position. This can also form an aldol which is having double bond at gamma position. That's why this simply forms aldol condensation reaction. That means this can form alpha beta unsaturated ketone as the final product. Now have a look. Can I say this is basically base catalyzed cross aldol condensation? This is also base catalyzed cross aldol. Cross means two different carbonyl compounds. Reaction between two different carbonyl compounds takes place. Now after that, if I write like this, this is also, my dear students, aromatic aldehyde without alpha hydrogen, but here this is what we call ester. This is ester having at least two acidic hydrogens, This is having what we call ester having at least two acidic hydrogens. Have a look. Whenever you are having a reaction in presence of base, it can also form a condensation product. Like that of aldol reaction. But whenever, if this is reaction number 1, this is reaction number 2, say for example this is reaction number 3, I can simply say 1 and 2, they are base catalyzed aldol condensation reactions. Base catalyzed aldol condensation. But if I say about what is 1, 2 and 3, 3 is not aldol condensation because this is not having alpha hydrogen is not having an aldehyde. Aldehyde is not having any alpha hydrogen. So this is known as what we call Claisen-Schmidt condensation. So what is Claisen-Schmidt condensation? Have a look. That condensation reaction in which either alpha beta unsaturated aldehyde or alpha beta unsaturated ketone or alpha beta unsaturated ester can be obtained by reacting aromatic aldehyde without alpha hydrogen with aliphatic aldehyde containing at least two alpha hydrogens, or aromatic aldehyde without any alpha hydrogen with aliphatic ketone containing at least two acidic hydrogens, or aromatic aldehyde without any alpha hydrogen with aliphatic ester with at least two acidic hydrogen. That reaction is known as Claisen-Schmidt, what we call condensation. Now, Claisen-Schmidt condensation is special type of base catalyzed cross aldol. This is base catalyzed cross aldol condensation. So, this is not base catalyzed cross aldol, but this is Clemmensen condensation, Clemmensen-Schmidt condensation, as well as cross aldol, base catalyzed cross aldol condensation. Now, I hope this is clear to each and everyone that what is basically simple, intermolecular and cross. Simple means when aldol reaction or condensation takes place between same types of aldehydes or ketones, and what we call when reaction takes place between two different types of aldehydes or two different types of carbonyl compounds or two different types of ketones, at that time we can simply call that as cross aldol condensation. Which type of product will be major? Major will be always cross aldol. If cross as well as self both can be formed as products, cross will be major, and among the cross, major product will be always enolate ion should be formed from more or less reactive carbonyl compound, and that enolate should attack to most reactive carbonyl compound, then it will get major product. After that, it's intramolecular aldol condensation. Have a look. For this, ring formation takes place, and ring which should be formed over here should be either 5 or 6 membered ring. 5 or 6 membered ring should be formed. I mean to say, if you are having a compound like this, CHO, then one, two, three, four, 5, and then it's like this. How will you form its, say aldol, and after that aldol reaction, after that aldol condensation product? First of all, OH minus. You have to find out alpha. This is alpha with respect to this. If this is alpha, so you have to show one hydrogen over here. So this becomes negative, this becomes positive. You have to show positive and negative. Now have a look. This H will go to oxygen. So first of all, you simply write down in this fashion, OH. Then this H goes to this. After that, it is CH2. 1, 2, 3. 1, then 2, and then 3. 3 CH2s will be there. After that, it is CH. This alpha can form a bond with this. After that, this CH is having CHO. So it will be like this. So this is alpha, this is beta. So beta hydroxy aldehyde is formed. That means this is aldol, but this is a cyclic one. After that, if this is heated, it will lose water molecule. It will lose hydrogen from alpha and what we call OH from beta position. So it will result in the formation of a 5-membered ring like this. This is a 5-membered ring. Here it will be, say double bond. Double bond will be here. After that, to this double bond, CHO is there. CHO is there. Have a look. So this is alpha, this is beta. Alpha beta unsaturated aldehyde is formed. So remember, it must form either 5-membered or 6-membered ring. Both can be, say aldehydes, both can be ketone, one can be aldehyde, another can be ketone. So you can show aldol condensation reaction. After that, there was a question in, in 2017. Question is like this. You are having X, which gives, say A. Now this is dehydrogenation reaction and this is A. A should be either aldehyde or a ketone, and dehydrogenation of this is basically an alcohol. It can be a primary alcohol, secondary or a tertiary, but we know tertiary can form alkene and primary will form aldehyde, secondary will form, say ketone, but this is Tolan's reagent and it gives silver mirror test. That means it must be an aldehyde as it gives silver mirror test. So this is an aldehyde. So this is aldehyde. So A is aldehyde. A is not ethanol. Ethanol is alcohol, so it's not that. Methoxymethane cannot be this. Methoxymethane cannot be this. Okay, A should be aldehyde, ethanol. So this is the answer. But if you want to see other as well, you can have a look. So this is ethanol. Say ethanol. So ethanol. So this can be ethanol. So it's exactly correct. After that, so OH minus, ethanol and OH minus. Have a look. Ethanol is like this. CH3, C double bond O and H. This is ethanol. When it is treated with OH minus and heat, that means it is aldol condensation. Write down another like this. It is CH double bond O. You know it's OH minus as well as heat is there. You have to lose water molecule over here. So the product of this is CH3, CH double bond CH, single bond C and H and O. That means it is alpha beta unsaturated aldehyde and its IUPAC name will be but 2En and 1 al. Yeah, you can write down but 2enal because that will be always at one position. So but 2enal. This is also correct. This is semicarbazide. When semicarbazide reacts with this O and 2 hydrogens will be lost. So its product will be CH3, then it is CH double bond. It's N, then NH, then C double bond O, then NH2. Now have a look. This is basically like this. We know C double bond O plus H2N. And then Z, it will lose this. So the value of Z, what was NH2? Z was NHCONH2. So NHCONH2. This is semicarbazone. So this is the right answer. This is the right answer. After that, another reaction is this. Which one of the following is not formed when acetone? Acetone is this one. CH3, C double bond O, CH3. This is acetone. When acetone reacts with 2-pentanone, pentanone is 2-pentanone is like this. So this is CH3, then C double bond O, then CH2, then CH2, and then CH3. 1, 2, 3, 4, 5. Okay, 2-pentanone. Okay, which cannot be formed in presence of dilute. That means you have to see which cannot be formed during aldol condensation. That means product is formed. You have to see retroaldol. How can you see? Have a look. This C double bond O, this is alpha. You have to first of all see alpha, because this is alpha, this is beta. Alpha beta unsaturated ketone or alpha beta unsaturated aldehyde will be obtained during condensation. So write down alpha and beta first. So this is alpha, this is beta. After that, this is alpha, this is beta. Alpha should be attached to C double bond O. Okay. Now break this bond. When you break this bond, give 2 hydrogens to alpha and give oxygen to beta. That means this is acetone, this is CH3CO, CH2, CH2, CH3. That means 1, 2, 3, 4, 5. That means this is pentan 2-on, yeah, 2 pentanone. That means it can be formed. It is, question is which is not formed. It can be formed. Now, after that you have to break this, give 2 hydrogens to alpha and give oxygen to this. This is acetone, this is CH3CO, CH3. Now, acetone and acetone. Yes, acetone can self-condense with each other and can form this. Yes, these two can form 4 products, 2 self products. One, it combines with another acetone, it combines with another pentan 2-on. Then this can combine with this, or this can combine with this. That means this can also be formed. After that, break this one. This is having oxygen and give 2 hydrogens to this. Now, this is 1, 2, 3, 4, 5. No, this cannot be formed. So this will be the answer. It cannot be formed. Now, if this is broken, give 2 hydrogens to this. This is acetone, give oxygen to this. This is pentan 2-on. 1, 2, 3, 4, 5. Yes, this can also be formed. So this cannot be formed. So this was asked in NEET 2022. Very, very, very easy question. After that, reaction between benzaldehyde and acetophenone. It's like this. Benzaldehyde, it's not having any alpha hydrogen, but acetophenone means this one. Acetophenone means this one. One is not having any alpha hydrogen, but this is having 2 acidic hydrogens. So this upon treatment will result in the formation of this product. CH double bond CH single bond C double bond O. This is known as aldol condensation. But which type of aldol condensation? These two are different aldehydes, this different carbonyl compounds. One is aldehyde, another is ketone. So this is cross aldol condensation. Is there any option? Yes, this is cross aldol condensation. This is not Cannizzaro, this is not cross Cannizzaro, this is not. This is aldol, but among aldol, most specific is cross aldol. So this is the right answer. So NEET 2020. You can see, you can have a look that this type of questions, these types of questions will be asked in NEET. Okay. Which of the following product is formed when cyclohexanone? Cyclohexanone is this one. Cyclohexanone is this one. Undergoes aldol condensation. That means you have to form another cyclohexanone. You have to form another cyclohexanone. What you have to do is, you have to remove 2 hydrogens. You have to remove 2 hydrogens from alpha, and you have to lose water, and you have to form double bond between alpha and carbonyl carbon. Is there any product? Yes, this is the final product. Yes, this is the final product. I hope this is clear to each and every one. Now, after that, it's Perkin condensation. It is Perkin condensation. Just a moment, light is back, so we can put on these lights as well. Now, have a look, my dear lovely students, have a look. Now, what is Perkin condensation? Very, very simple. If you are having aromatic aldehyde without acidic hydrogen, aromatic aldehyde without acidic hydrogen, and you are having aliphatic acid anhydride, you are having aliphatic acid anhydride containing at least 2 alpha acidic hydrogens, there will be a sort of condensation reaction like that of aldol, but this reaction takes place in presence of a base, and that base is basically sodium salt of acid, from which anhydride has been obtained at a temperature of 453 Kelvin. What will happen? Water will be lost. Water will be lost, and there will be a condensation product like this: alpha beta unsaturated anhydride plus water. But this water will simply hydrolyze this anhydride. And here will be simply breakdown of this bond. OH will go to this, H will go to this. So in this reaction we get alpha beta unsaturated carboxylic acid. So this is alpha, this is beta unsaturated acid. Alpha beta unsaturated acid will be the product. So what is Perkin condensation? It's a reaction of aldehyde without alpha hydrogen with aliphatic acid anhydride having at least 2 alpha acidic hydrogens, in which final or end product is alpha beta unsaturated carboxylic acid. That is Perkin condensation. After that, next reaction is benzoin condensation. What is benzoin condensation? It is basically self-condensation of benzaldehyde. It is self-condensation between, I mean to say, benzaldehyde. Self-condensation between benzaldehyde. Have a look. This is partial positive, partial negative. And here, this can be what we call a partial positive, partial negative. This is also partial negative. Just write down this H. First of all, you broke this bond towards this. O becomes O negative. This H goes to O. That means it will result in the formation, and this reaction takes place in presence of alcoholic potassium cyanide. It will result in the formation of alpha hydroxy CHOH, alpha hydroxy ketone. Have a look. This is ketonic functional group, this is alpha. So alpha hydroxy ketone obtained from benzaldehyde is known as benzoin, and that condensation in which benzaldehyde undergoes self-condensation in presence of alcoholic potassium cyanide results in the formation of benzoin is known as benzoin condensation. Another is Cannizzoro's reaction. Now have a look. This Cannizzaro reaction once again is basically of 2 types. One is intermolecular. Another is intramolecular. This intermolecular is once again of 2 types. One is simple or self. Another is what we call mixed or crossed. And have a look. This reaction is shown by those types of aldehydes which do not have any alpha hydrogen. Basically, these types of aldehydes do not have any alpha acidic hydrogens. Ketones do not show this reaction. And remember, this reaction is basically a disproportionation. This one. That means disproportionation. That means one type of molecule is, one molecule is oxidized and another same type of molecule is reduced. But here, one molecule is different, another is different. Hence, here oxidation reduction will take place. And here, we generally use concentrated bases or what we call 50% NaOH. So it can be NaOH, it can be KOH, but it should be concentrated. Have a look what will be the reaction. If we talk about self or simple intermolecular Cannizzaro reaction, what will be the product over here? This is CH3, CHO. We know it's intermolecular, that means there must be at least 2 same types of molecules. So when there are same types of molecules, what will be the product over here? And reaction takes place in presence of concentrated base, but our aldehyde must not contain any alpha hydrogen. This is having alpha hydrogen, this is having alpha hydrogen. So we don't need these types of aldehydes right now. That's why I will write down HCHO. Just you have to oxidize one CHO group. Just oxidize one CHO group into COO negative. And here positive part is Na, so CONA. That means convert CHO, one CHO into CONA, and another, you have to break down this like this. Have a look, have a look. Another, you have to break down one bond, add hydrogen and hydrogen over here. That means it becomes CH3OH. C double bond O, you have to convert C double bond O into CHOH. You have to convert this into this. Have a look. But this is the difference. This is the difference. Convert C double bond O into CHOH. That means this is CH3OH. Similarly, if you are having this one, benzaldehyde, this is also not having any alpha hydrogen or acidic hydrogen. So what will be the product over here? Have a look. This is very easy. Convert one into sodium salt of acid. I mean, say you have to oxidize one and reduce one. You have to oxidize formaldehyde, reduce formaldehyde, disproportionation. Oxidize benzaldehyde, oxidize, reduce benzaldehyde, disproportionation. Now, what we have to do is, what is the trick? Convert CHO into COONA. Simple. And another, convert this C double bond O into CHOH. Then it will become like this. CHOH, another H is there. That means it becomes CH2OH. Very, very easy. Similarly, if you write like this, CH3, then C, CH3, then CH3, then CHO. What is the trick? Convert one CHO group into COONA and convert another C double bond O into CHOH. Very easy trick. Now, convert this CHO into CONA and convert another C double bond O into CHOH. So it will become CH3 whole 3C. Can I write down? CH3 whole 3C, then it is COONA plus CH3 whole 3C. This one. After that, it is CHOH and then it's H. So you have to convert CHO into CONA and you have to convert C double bond O into CHOH. Now, what is the mechanism of this reaction? Have a look. This is very, very important reaction once again. So mechanism is like this. First of all, I will show mechanism with the help of HCHO. When it is treated with NaOH or OH minus base, base will act here as a nucleophile because it cannot abstract any hydrogen as there is no acidic hydrogen. So first of all, nucleophilic attack will take place. So first of all, it's a nucleophilic addition reaction, simple. Now it will result in the formation of HCHO having negative charge and here it will be OH. Now have a look, have a look. This O minus will form double bond and OH will leave, but OH is not a good leaving group. But if we remove OH, it will go back, but we need to proceed reaction in forward direction. That's why it will form double bond and it will simply, this hydrogen will be lost. Now, when this hydrogen will be lost, where will it go? It will be transferred basically to another, it will be transferred as H minus to another same type of aldehyde in case of simple what we call our self Cannizzaro reaction, but in case of cross Cannizzaro reaction, it will go to another different type of molecule. Have a look. So in this step, hydride transfer takes place, and this hydride transfer is the slowest step, hence this is the rate determining step of the reaction. What will happen? Now it will become HC double bond O. Now this H has been transferred to this, so there is OH here. So acid will form and this becomes HCH, it becomes O negative here, hydride, that means H will come. After that, we know this is acid, it will lose H positive and that H positive will be abstracted by this. That means hydrogen positive, that means proton transfer takes place. Now it will become HCO O negative and that will become HCHHO, what we call H. Now the question is, I have written OH minus. If I have written NaOH, then this was O minus Na positive, then this was O minus Na positive, and this is O minus Na positive. So this is oxidization product and this is the reduction product. So one formaldehyde is oxidized, another is reduced, hence this is known as self-oxidation reduction. That means this is known as disproportionation reaction. But if same type of reaction takes place between different aldehydes, suppose one aldehyde is benzaldehyde, another aldehyde is formaldehyde, both are different, and in case of cross-Kenies-Oro reaction, none of the aldehydes must contain any acidic hydrogen or any alpha hydrogen. Because if any one is having alpha hydrogen, then it will become cross-aldol condensation. Now here, cross-Kenies-Oro reaction, what will happen? What will happen? You have to oxidize one and reduce one. Now the question is, can I say nucleophilic addition reaction among these two? Can I say if we talk about nucleophilic addition reaction, this is more reactive, and can I say this is least reactive? Why this is least reactive or less reactive? If this is more reactive, this is less reactive. Now the question is, why this is less reactive? Because this is attached to this phenyl ring which shows plus M effect. That means it is electron donating with respect to this. There is no electron donating group. More the electron donating group, lesser will be the nucleophilic addition reaction. So more reactive. You have to oxidize more reactive. Oxidize this. And you have to reduce. You have to reduce least reactive. Means form alcohol from this and form acid from this. That means oxidize this to HCONA. So it becomes HCOONA. Oxidation. This is oxidation. Now, you have to reduce this, convert C double bond O into CHOH. That means you have to add hydrogen over here. So convert this into CHOH. So it becomes CH2OH. So you have to reduce this, means you have to form alcohol from this, and you have to oxidize this. That means you have to form, salt of carboxylic acid from this. Similarly, if you have question like this, one is benzaldehyde, another is same benzaldehyde but it's having methyl at para position. Methyl becomes plus M. So this becomes less reactive due to electron donating group, less reactive, and this becomes more reactive. So more reactive, you have to oxidize more reactive. This is more reactive. This is more reactive. What you have to do is, you have to oxidize more reactive. That means it's very simple now. In presence of NaOH, concentrated NaOH, you have to simply form CONA from this, and you have to form alcohol from this one. Now it is CH2OH. So this is very easy. After that we are having intramolecular. We are having intramolecular Kenies-Oro reaction. We are having intramolecular Kenies-Oro's reaction. In that, it's a very simple reaction. Have a look. As both carbonyl are of same type, so oxidize one C double bond O and reduce one. That means if you oxidize this one, it becomes C double bond O ONA. Then you have to reduce this, it becomes CH2OH. Because it becomes CHOH and H is already there, so CH2OH. Similarly, if you are having like this, among these two, this is more reactive, this is less reactive, because electron donating group is attached to this. So you have to oxidize more reactive. That means it becomes C double bond O ONA, and you have to reduce this one. That means C double bond O becomes CHOH and CH3 is attached to this. So this is intramolecular Kenies-Oro reaction. This is very simple. Very simple reaction. After that, another reaction is, this is known as Tischenko reaction. Let me tell you that all types of aldehyde show this reaction. all types of aldehydes show this reaction, whether that aldehyde contains alpha hydrogen or not. For example, if you are having this, what we have to do is, if you are having this one, what you have to do, this is an aldehyde having alpha hydrogen. This can be shown by an aldehyde with alpha hydrogen or aldehyde without alpha hydrogen. What you have to do is, you have to react such aldehydes with aluminium ethoxide and form and oxidize one into carboxylic acid and reduce another into alcohol. Say for example, you oxidize this into carboxylic acid and reduce this into what we call alcohol. So it becomes CH2OH, CH3. Can I write like this? CH2OH and CH3. First form this carboxylic acid and alcohol. After that, remove OH from carboxylic acid and H from what we call alcohol and simply lose water molecule and form ester. So that reaction in which aldehyde with or without alpha hydrogen form ester in presence of aluminium ethoxide is known as Tischenko reaction. So final product of Tischenko reaction is ester actually. After that, electrophilic substitution reactions of aldehyde are ketones. Now have a look. Whenever you are having C double bond O, if it is having H, then it is aldehyde. If it is having R, then it is ketone. Now, if halogenation takes place, it always takes place in presence of anhydrous AlCl3, but when it is in excess. Otherwise, its side chain halogenation takes place. So, for nuclear halogenation, for electrophilic substitution halogenation, you have to remember that this AlCl3 or Lewis acid must be present in excess. After that, if you are treating this with concentrated HNO3 and concentrated H2SO4, I mean say nitration, or you are simply having sulfonation reaction, say for example H2SO4. First of all, we know that this CHO or COR, I mean say aldehyde or ketonic group, is electron withdrawing. It decreases overall electron density of the ring and it deactivates reaction for electrophilic substitution reaction. That means rate of electrophilic substitution reaction will be very less. But if we want to carry out electrophilic substitution reaction, remember, it withdraws electrons from ortho and para. That means ortho and para becomes electron deficient. So meta is by default becomes rich. So electrophile from these reactions, say for example, X positive from this, NO2 positive from this, and SO3 from this, they will go to meta position. Hence, product of this reaction will be like this. So C double bond O, whether it is H or R, I mean say whether it's aldehyde or ketone, halogen will be introduced at meta position. Similarly, electrophile will be introduced at meta position, and that electrophile is nitro. So nitration, that is halogenation. Here, sulfonic acid will be, I mean say sulfonic acid group will be introduced at meta position. Hence, this is known as sulfonation reaction. So this was all about aldehydes and ketones. Now, have a look on carboxylic acid. It will take maximum 30 to 40 minutes so that this chapter will be completed. Now, another is methods of preparation of carboxylic acid from primary alcohols and aldehydes. We know if we are having primary alcohols, we want to convert primary alcohol into carboxylic acid. We use strong oxidizing agents. First, it will form aldehyde. By removing hydrogen from functional group and from what we call alpha hydrogen. But this aldehyde, this is primary alcohol. This aldehyde cannot be isolated, cannot be obtained because strong oxidizing agent, once aldehyde is formed, strong oxidizing agent will convert this aldehyde into carboxylic acid having same number of carbon atoms as that of the parent, what we call primary alcohol. So in this fashion, we can convert primary alcohol to carboxylic acid, or we can convert aldehyde to carboxylic acid by using strong oxidizing agents. We have already studied this in alcohols. After that, from alkyl benzene, and suitable alkenes. Have a look. From alkyl benzene, for example, you are having a benzene, I mean say, to which alkyl group is attached. Remember, it can be any alkyl, but this alkyl must contain at least one hydrogen at benzylic position. Upon treatment with strong oxidizing agents, this alkyl group is converted to COOH. Irrespective of whether this alkyl is smaller alkyl or larger alkyl, hardly matters, convert alkyl into COOH. For example, if you are having, but remember this alkyl must contain at least one hydrogen at benzylic position. That means to that carbon which is directly attached to benzene ring. For example, you are having this. And suppose it's treated with a strong oxidizing agent KMNO4 and KOH. Now it will form, this alkyl will be converted to COOH. But remember, this is acid, this is base. This base will abstract this H as H positive and it will result in the formation of CO minus. As base is having K positive, that means it will first form this one. But after acidification, say for example, it is treated with dilute HCl, CO minus will abstract H from this and KCl will be lost. That means it will result in the formation of COOH. But if same reagent is used, or what we call other, I mean say strong strong oxidizing agent in acidic medium are used. Say for example, KMNO4 KOH is used, followed by acidification. Then you just convert that alkyl directly into COOH. So it will result in the formation of COH. Similarly, if you are having other alkyl benzene like CH2, CH3. For example, you are having CH, CH3, CH3. You are having C, CH3, CH3, CH3. Have a look, my dear lovely students. Have a look. Whenever such alkyl benzene, they are treated with strong oxidizing agents in acidic medium. I will write down now acidic medium. In basic medium, it will form salt, but in acidic medium, there will directly, I will write down no benzoic acid formation takes place. Now tell me why. No benzoic acid formation takes place. Now, reason, what is the reason formation takes place? Because we need that type of alkyl which contains at least one hydrogen to this benzylic position. This is not having any hydrogen, so no benzoic acid formation. But as this is having one hydrogen, this is having one hydrogen, convert this into benzoic acid. Convert this into benzoic acid. So irrespective of size of alkyl group, you have to convert alkyl group into COH. So this is what we call the product formation. Similarly, if we write like this, this is CH3, this is CH3. This alkyl group is converted to COH, this alkyl group is converted to COH. That means upon treatment with strong oxidizing agent, it will result in the formation of COOH and COH. Similarly, if these CH3 groups are present at meta position, both alkyl groups will be converted to COH. Similarly, if they are present at para position, both will be converted to, I mean say, alkyl group. If you are having an alkyl group like this, it's attached to this ring as well. So what we have to see is, that means you have to check first of all reaction taking place in acidic medium or basic medium. If basic medium is there, you have to form CO minus Na positive, K positive depending upon the base. You have to form directly acid in acidic medium. So what will be the product? This is phthalic acid. Now this product is known as isophthalic acid and this product is known as terephthalic acid. Have a look, have a look, have a look. Now can I say this is also having CH2 group. I mean say this is having benzylic carbon is there. Benzylic carbon is there. So it's having one hydrogen. So convert that into COH. Similarly, this is also a benzylic carbon which is attached to benzene ring. It's also having hydrogen. So convert this into COH. So this is phthalic acid. So this was all about when alkyl benzene is treated with, say strong acids, what will happen. Now, from nitriles or amides, have a look, my dear students. This is nitrile. Nitrile upon hydrolysis. Nitrile upon hydrolysis, whether in acidic medium or in basic medium. What you have to do is, you have to break one bond of this, add hydrogen to nitrogen and add OH to, say carbon. Second bond, add hydrogen and OH to this. Third bond, add hydrogen here, OH here. But you know, to this carbon, 2 OH will lose water molecule and become C double bond O. So the final product becomes RCOOH. So this is what we call hydrolysis. So hydrolysis of cyanide or nitrile results in the formation of what we call carboxylic acid. But, if you are having cyanide and it is written there that it is partial hydrolysis. If it is written partial hydrolysis, if it is written hydrolysis, then it is complete hydrolysis. But if it is written partial hydrolysis, then what you have to do is, have a look. You have to break only 2 bonds and add 2 hydrogens over here, 2 OH over here. So that means it will result in the formation of RCNH2. Here 2 OH will lose water molecule and become amide. That means partial hydrolysis gives amide, but hydrolysis of cyanide gives what we call, or nitrile gives, carboxylic acid having same number of carbon atoms. This is hydrolysis or complete hydrolysis. If hydrolysis is written, remember it is complete hydrolysis. Otherwise, if it is written partial hydrolysis, then you have to do this. Now, if you have to remember, if amide is there, this amide can be further hydrolyzed. It can be further hydrolyzed in presence of acid or base. It can be hydrolyzed, give H to this, OH to this, so it can form carboxylic acid. So here to here it's partial hydrolysis, from here to here it's complete hydrolysis. Whether complete hydrolysis is given or hydrolysis is given, it's one and the same. So upon hydrolysis or complete hydrolysis, carboxylic acid will be the product, but upon partial hydrolysis, amide will be the product formed from what we call nitriles. After that, from Grignard's reagent, have a look, my dear lovely students. It's RMgX. When it is treated with carbon dioxide, this is having negative charge, this is having positive charge. So it will attack, it will act as a nucleophile, will attack to this carbon. One of the pi bonds will be broken out. So in presence of dry ether, what will happen? Have a look. It will result in the formation of R will form bond with this C. This C has already a double bond with oxygen and it will form one O negative with, say this one, and then positive charge will be simply MgX will be attracted to this negative charge. This is what we call an adduct, and after that it will undergo hydrolysis. It will undergo hydrolysis. This bond will be broken, give H to this and OH to this, we will get carboxylic acid. So carboxylic acid can be formed. But remember, this carboxylic acid is having one carbon greater than the value of this R of Grignard's reagent. Remember this. After that, we are having a question, RMgX plus CO in presence of dry ether gives. So obviously it will form R, then it will form COO negative and MgX with a positive charge. So this is what we call our Y. So RCO minus MgX positive. So this is R3, no. This is RCO minus X positive, no. RCO whole to Mg, no. So it's like this. Have a look. It's RCO minus MgX. So this was asked in NEET 2022. A very easy question. After that, from acyl halide and anhydride, have a look, my dear lovely students. This is acyl halide. Say for example acyl chloride. Now another is acid anhydride. It's like this, R C double bond O, O C double bond O and R. Remember, whenever hydrolysis take place, whenever hydrolysis takes place. Hydrolysis means you have to break down. You have to break down. Whenever you break down, what you have to break? You have to break this CX bond. Acyl group has to be broken. And after that, negative part of this nucleophile goes to this. Negative part of this goes to this. These reactions are known as nucleophilic acyl substitution. That means these are nucleophilic substitution reactions taking place at acyl group. Nucleophilic substitution reactions. So the product will be RCOOH. And here it will be RCOOH. If a reaction takes place in acidic medium, acid in acidic medium remain as such. But if reaction takes place in basic medium, what will base do? Base will abstract this H and form salt from carboxylic acid. That's the only difference. Now, after that, next reaction is from esters. Very good reaction. This is ester. Ester. I will show you. If I want a reaction in acidic as well as basic medium, have a look. What will be the product over here? Now, first of all, let me show you what will happen if it is water. What will happen if it is water? Now, I will give OH to this, H to this. That means it will result in the formation of RCOOH plus R prime OH in neutral medium or in acidic medium. What will happen in basic medium? Say for example, NaOH is the base. That means it is Na positive and OH minus. Among water and OH minus, it is OH minus which is stronger nucleophile. That means it will first form, have a look, RCOOH. But OH means carboxylic acid has been formed. After that, this base will abstract that and it will form sodium salt of acid. That means here sodium salt of acid will be formed and here it will be R prime OH. Now, this reaction in which this is formed, if R is, if R is large, for example, C17H35 etc. C17H35 etc. Then we can simply call this as soap. So this reaction, so at that time RCOO minus Na positive can be an example of soap, and that reaction during which soap is formed, this reaction during which soap can be formed, basic hydrolysis of ester is known as saponification. Basic hydrolysis of ester is known as saponification reaction. It's known as saponification reaction. One more reaction, say for example, if you are having an ester and you want to react it with alcohol. This is the negative part of alcohol and this is the positive part of alcohol. So you have to break this, you have to give negative part to this and positive part to this. OR minus is the negative part, OR part to this and H part to this. Have a look. Negative part is OR double prime and positive part to this. What will be the product? What will be the product? Product formation will be, once again, from this ester, another ester will be formed. That means RCO, O double R plus R prime OH. This reaction in which ester and alcohol reacts and forms another ester and alcohol, this is known as trans-esterification. So trans-esterification. This is known as trans-esterification. I hope this is clear to everyone. After that, these are very simple reactions. Now, chemical reactions of carboxylic acids. Now, first reaction with metal. Whenever carboxylic acid react with metal, say for example sodium, potassium, calcium, magnesium, zinc, what will happen? It will result in the formation of sodium salt, potassium salt. That means it will result in the formation of salt of that metal with, this. That means it will form salt. That means it will form RCONA and hydrogen gas will be evolved. If I want to, balance the reaction, I will write half of H2. So it will simply result in the formation of salt of this, but salt with that metal with which it has to react and hydrogen gas will be evolved. So this is the reaction with metal. Very, very, very easy reaction. After that, reaction with carbonates and bicarbonates. First of all, this reaction is shown. This reaction is shown by those acids which are stronger than carbonic acid. For example, this reaction can be shown by sulfonic acid, this can be shown by picric acid, this can be shown by squaric acid, this can be shown by dinitrophenols, this can be shown by carboxylic acid, even this can be shown by paranitrophenol. I mean to say for example, we are having carboxylic acid. This cannot be shown by phenol. This reaction cannot be shown by phenol. This cannot be shown by alcohol. I mean say this cannot be shown by orthonitrophenol, metanitrophenol, because those acids are weaker acids than carbonic acid. Now, whenever it is treated with, say for example, sodium bicarbonate, what will happen? This is having negative charge, this is having positive charge. This will abstract H positive and this will lose H positive. It will result in the formation of H2CO3 and RCONA. So it will form sodium salt of acid plus H2CO3, carbonic acid, but it will further be converted to carbon dioxide plus water. So there will be effervescence because carbon dioxide gas bubbles will be formed there. So carbon dioxide gas will be evolved, effervescence will be there. But effervescence or carbon dioxide will be formed only if this acid is stronger acid than carbonic acid. We know carboxylic acid is stronger acid than carbonic acid, but normal phenol is weaker acid than this. That's why phenol cannot show this reaction. Carboxylic acids can show this reaction. That's why this reaction can be used as a distinguishing test between carboxylic acid and phenol. But in general, this can be used as a distinguishing test between those acids which are stronger acids than carbonic acid and those acids which are weaker acids than carbonic acid. Similarly, if I write RCOOH twice plus Na2CO3, you know, this is having two negative charges, this is having one positive, another Na is having another positive. So first of all, CO3 2 minus will abstract H positive from one acid, becomes HCO3. Then HCO3 will abstract another hydrogen from another acid, will become H2CO3. So it will result in the formation of twice RCOONA plus H2CO3. But this H2CO3 will evolve carbon dioxide gas over here. So acids, stronger acids than carbonic acid will show this reaction, will show effervescence and will give sodium bicarbonate or sodium carbonate test. After that, reaction with alkalis. Whenever you are having an acid and if it results with alkali, say for example a strong base like NaOH or a base like NH4OH, now acid and base will neutralize together and salt formation will take place. That means its positive part and negative part, positive and negative, will be simply, replace this positive part by Na. That means it will result in the formation of RCONA, and then positive part of that and negative part of this will combine. Similarly, it will form ammonium salt of carboxylic acid plus water. Very easy reactions. After that, formation of anhydride. Now have a look. It's RC double bond O. Then you are having OH. Similarly, another C double bond O and then O and H. So here water will be lost, but with the help of dehydrating agents like P2O5 is a strong dehydrating agent, or concentrated H2SO4 is a dehydrating agent. When these carboxylic acids are heated with these dehydrating agents, they will result in the formation of RC double bond O, then C double bond O, or anhydride. A very, very easy reaction. After that, another reaction is formation of acyl chloride. Have a look. Whenever you are having RCOOH and you react it with like this. One, you react with it with PCl5, PCl3 or SOCl2. PCl3, PCl5, PCl3 or SOCl2. What will happen? Just replace this OH by negative part of this. That means nucleophilic substitution reaction is this. So it will result in the formation of RCOCl. This will also result in the formation of RCOCl. This will also result in the formation of RCOCl. But here side products will be SO2 and HCl. That will be side products will be gaseous side products. So they will evolve and this will be formed in pure form. So this is the better method to prepare RCOCl or acyl chloride from carboxylic acid. After that, another is formation of ester. We have already studied this reaction. This is known as esterification reaction. We have studied this reaction in alcohols, and it's what we call a reversible reaction, can take place either in presence of concentrated H2SO4 or HCl. But if reaction takes place in HCl, then it's known as Fischer-Sippier esterification. We have already discussed its mechanism as well. So you can go through alcohols, I mean say last chapter, last session. So it's already there. So OH in water, O comes from, I mean say O came from this carboxylic acid, and water, OH came from carboxylic acid and H came from alcohol. Or you can say O of water came from carboxylic acid, and it will result in the formation of this, I mean say ester. After that, yes, one more thing is that rate of esterification is inversely proportional to steric crowding. It's inversely proportional to steric crowding. I have already told you this in alcohols as well. So if you increase the value of this R or you increase the value of R prime, rate of esterification will decrease. After that, it's formation of amide. It's very simple reaction. Whenever you are having a carboxylic acid and you treat carboxylic acid, remember, you treat carboxylic acid with ammonia and heat. At that time you have to lose water molecule, H2 and water, H and OH, that means water will be lost and it will result in the formation of amide. But, if you are having a reaction like this, there is no heat, then first form ammonium salt of carboxylic acid. After that, upon heating, it will lose water molecule and result in the formation of amide. In nutshell, carboxylic acid on treatment with ammonia and heat results in the formation of amide. Now here, it's treated with ammonia. So ammonia will result in the formation of ammonium salt. That means it will result in the formation of CONH4. Similarly, this will also form CONH4. Upon heating, this will lose water molecule and it will become amide, CONH2. This is CONH2. This is known as phthalimide. But upon strong heating, ammonia is lost. Remember, it will lose ammonia, that means NH2 from one carbon and H from nitrogen. So it will form phthalimide. It will be C double bond O, then it is NH, then it is C double bond O. Have a look. This C loses NH2, this N loses H. So one bond will be lost over here or one here. So they will form bond with each other. This is known as phthalimide. So this is imide, this is amide. Remember this. Okay. After that, okay, the question from NEET 2019. The product of the following reaction is, so it's this phthalic acid is treated with ammonia and strong heating. Strong heating is there. That means convert this into CONH4, then water will be lost, CONH2, then strong heating is there, then ammonia will also be lost, then it will form phthalimide. That means this one is the product of this reaction. After that, It's reduction. Reduction of what? Carboxylic acid to alkene. Simple. Whenever you have to reduce this carboxylic acid to alkene, the best reagent is HI in presence of red phosphorus. You have to simply convert this COH into CH3. That's it. So this is alkane. After that, reduction to alcohols. From carboxylic acid, if you want alcohol, we have already studied this reaction. If you want alcohol, if you want to convert this into alcohol, it will be CH2OH, and reducing agent is either lithium aluminium hydride followed by hydrolysis, or it will be B2H6 followed by hydrolysis. We have already studied this in, alcohols. Okay, these two types of reactions I have already discussed. I have already discussed these two types of reactions with you in chapter hydrocarbon. But still, now, if you are having sodium salt of carboxylic acid, first treat carboxylic acid with NaOH, it will result in the formation of sodium salt. Then NaOH, soda lime means NaOH and CaO. NaOH and CO in the ratio of 3:1. What will happen? Loss Na2CO3. Oh, you have to loss Na2CO3. And a result in the formation of, break this bond, form carbanion. I have already told you that. Then R minus will abstract this H, so it will result in the formation of this. We have discussed this reaction in detail there. Now using Kolb's electrolysis, we know RCOONA or RCOK twice plus twice H2O upon electrolysis results in the formation of RR, that means alkane at anode. We have already discussed the reaction. And then it will evolve carbon dioxide gas, that too at anode. After that, hydrogen gas will be evolved at cathode, and pH of the solution will be basic. That means pH will be greater than 7. We have already discussed this. But if this R is H, that means if it is sodium formate, sodium methanoate, then this will be hydrogen. That means at that time hydrogen will be evolved at cathode as well as anode as well. We have already discussed this. After that, the question was asked in NEET 2021. CH3CH2CO minus NaOH. Okay, here you have to check. That means this is having CH3 instead of CH2. That means addition of hydrogen. So carboxylic acid or sodium salt is converted into alkane. That means decarboxylation has been taken place. Decarboxylation takes place either by using soda lime or electrolysis. Here NaOH is there, but for soda lime this note of interrogation must be CaO. That means this is the right option. After that, reaction of alkyl group, that means it is halogenation. Halogenation. Have a look. First of all, this reaction is shown. This reaction is shown by those carboxylic acids, which contain at least one alpha hydrogen. That means, say for example, if I write CH3 C double bond OH, what we have to do is a very simple reaction. Halogenation in presence of red phosphorus takes place, followed by, in presence of this water. What we have to do, just replace hydrogen of alpha by halogen. That means replace one hydrogen by one halogen, so this will be the product. And this reaction is known as HVZ reaction. That means it is Helmholtz-Zelensky reaction. Helmholtz-Zelensky reaction. Now, this X is either chlorine or bromine. That means we have to do alpha chlorination or alpha bromination. Now, CH3COH is there. if reaction first takes place in presence of chlorine and red phosphorus. Remember, if water is not given, take water as solvent. If it is given, then it's okay. If it is not given, take water as solvent. Remove first Cl, first H by first Cl. After that, if this Cl2 is taken in excess, then what you have to do is replace another hydrogen by chlorine. That means it will become Cl2. Then replace another hydrogen. But at alpha position, you have to replace another hydrogen. So it will become CCl3, then it will become Cl3C, then COOH. So this is alpha chlorination or alpha bromination. That means chlorination or bromination taking place at alpha position. That means you have to replace alpha hydrogen by chlorine or bromine, one by one, depending upon is chlorine or bromine taken in excess or not. After that, reactions of aryl group. That means we know COH is once again electron withdrawing group. That means it's a meta-directing group. If it is meta-directing group, so electrophilic substitution reaction takes place at meta position whenever it takes place. So if I write three types of reactions over here, number one, halogenation in presence of, for example, AlCl3 anhydrous. Nitration, that means HNO3 concentrated and H2SO4 nitrating mixture, say. And if I take what we call H2SO4, that means sulfonation. What will be the electrophile of this? It will be X positive. Its electrophile will be NO2 positive. And its electrophile will be SO3. Finally, it becomes SO3H. Then the product of this reaction will be like this. It will be COOH. Then halogen will be introduced at meta position. In this reaction, nitro group will be introduced at meta position. And in this reaction, SO3 becomes SO3H. That means SO3H will be introduced at meta position. I hope this is clear to each and every one. Now, this was all about aldehyde, ketone and carboxylic acid. So thank you very, very much for your patience to listen this whole chapter. I hope this was clear to everyone. Mathi says, thank you, sir, for explaining this chapter clearly. But thanks to you, because you have been with me since 8. So thank you and God bless you all. I hope this is clear to everyone. I am preparing for NEET. If I got into, otherwise I will do my PhD. No, you just work hard. Everything is easy. You can crack NEET examinations very easily, but you must have, you have to be very much sincere with your studies. That's it. Okay. Is this clear to each and everyone? Let me know in the chats. How was the session? I will end up this session and I want a reply from each and everyone, but in the comments, not here, in the comments at the end of the session. And love you, sir. Thank you very much. Sana Nusrat Fazal, thank you very much. Okay, so that's it for today. So we'll see you in next session and with amines, to say. So till then, take care and God bless you all. Good night.